welcome our guest, sir.
Yeah.
Okay, okay.
We will
All right.
welcome. He's in the heart. You just let him share the slides till time.
Okay, sir. Okay, sir.
Let him share the slide. Just down, sir. You can Shenoy is up,
Yeah.
you just down. Share the slides.
Yes. Yeah, but he's doing that. Yeah, I got it.
Good. Okay.
Yeah. Hello, everybody, and a very good morning to our respected speakers, honorable dignitaries, all the peers, patrons, and participants. This is Duraksha, your host for today. I feel privileged to extend my warm welcome to all of you on behalf of Department of Physics, NIT Srinagar. As you all know, today marks the end of this short-term course, but then endings are to be celebrated for they precede new beginnings, isn't it? I would also want to offer gratitude to our participants for making this short-term course a success for all of us. Together in this journey, we learned a lot and made it memorable for all of us. So, huge thank you to all of you. So now starting with our ninth session for day 5, I would like to introduce our speaker, Professor Shenoy. Professor Shenoy received his MSc in Physics in 1979 from Mysore University and the PhD in the field of fiber and integrated optics from IIT Delhi in 1987. He joined the faculty of IIT Delhi in 1988, where he is currently a professor of physics working in the area of fiber and integrated optics. He was a visiting scientist with the Department of Electrical and Electronic Engineering, University of Glasgow, United Kingdom. He's an author of about 50 research papers and is a co-editor of the book Fiber Optics Through Experiments. His current research interests are in the area of optical amplifiers and nonlinear optical devices. I would now request Professor Shenoy to kindly start with this session. Over to you, sir.
Thank you. Direction, very good.
Thank you very much. We are right on time. So, first of all, let me thank Dr. Shah and his team for giving me this opportunity to speak to all of you. And today we are starting with the optoelectronics. And I must warn you that my talk is going to be almost like a slideshow. That's a rapid slideshow. It's like, when we were children, then we used to see slideshows of Mumbai Dekho, Delhi Dekho, Calcutta Dekho, slide after slide. They will show, ye hai Lal Killa, ye hai Qutub Minar, like that. But at the same time, why I opted for this is because you have already attended 4 days of good amount of talks on semiconductors and devices, fabrication aspects, and so on. Therefore, you would be able to pick it up very fast. That's also the reason why I thought, let me give an overview and a very quick one. Right, so let me expand my screen here. So hope you are able to see it. You are able to see the full screen?
Yes, sir. Yes.
Yes, sir.
Okay. So semiconductor optoelectronics. So optoelectronics, let me start. Optoelectronics, which refers to optics plus electronics, it primarily deals with the electronic devices which involve interaction with light. It's a part of optical engineering. It involves both science and engineering, very much interdisciplinary in nature. And optoelectronic devices are widely used in optical communication and signal processing. Some of the optoelectronic devices are very familiar ones: light emitting diode, double heterostructure laser diodes, quantum well, quantum wire, and quantum dot lasers, photodetectors, electroabsorption modulators, quantum cascade lasers, and the list goes on. So the outline of my talk would be, I would briefly introduce semiconductor optoelectronic materials, then go over to semiconductor heterostructures, double heterostructure lasers, certain single frequency laser devices, quantum well lasers, just touch upon device packages, and finally end with a little discussion on light emitting diodes and photodetectors. So this is, as I said, it's a very quick review, but you can see the full detailed course, which is freely available on the NPTEL website, a full video course of 46 lectures. And you can see the link, or just Google my name, you will get the link for all of them. I had also been conducting the Semiconductor Optoelectronic MOOCs. So this I had last semester, and this semester I held another MOOC, Lasers and Introduction. These are all AICTE approved FDB courses, and you can see for the details in NPTEL website. All right, let's go to Semiconductor Optoelectronic Materials. So it's a part of the periodic table which is shown here. Group 3, Group 2, Group 3, 4, 5, and 6. I have taken only those parts where most of the optoelectronic materials are located. As you know, the Group 4 elements, silicon and germanium, are widely used semiconductors. And Group 3, 5, one element from Group 3, one element from Group 5, such as gallium arsenide, aluminum arsenide, indium phosphide, indium arsenide. These are very important materials for optoelectronics. And there are also, you can have Group 2 and 6. So finally, the electronic configuration should form an octet, that is 4 plus 4 or 2 plus 6 or 3 plus 5. It has to form an 8 to form a stable compound. All right. So the energy band diagram, what is shown here, you are very familiar with this. These are direct band gap semiconductors and indirect band gap semiconductors. What is shown is the EK diagram. And typically, gallium arsenide is a direct band gap semiconductor, and silicon is an indirect band gap semiconductor. Now, this table lists certain materials, most common materials in optoelectronics. These are the binary semiconductors, elemental semiconductors, their band gaps, and the band gap wavelengths, and the type of band gap. I'm sure you are familiar with most of them. Now, a third class of semiconductors is alloy semiconductors. Namely, you have one element is a fraction of, for example, if you start with gallium arsenide, a fraction Fx of gallium is replaced by aluminum from the same group, from the group 3, to make a ternary compound. So gallium, aluminum, arsenide. Similarly, you can have quaternary compounds. For example, indium, gallium, arsenide, phosphide. You start with indium phosphide substrate. X fraction of indium is replaced by gallium, and Y fraction of phosphorus is replaced by arsenic, and thereby forming a quaternary compound. There are various reasons why we go for such ternary and quaternary compounds, but I will just illustrate one of them. One of them is for band gap modification. If you see the variation of direct and indirect band gaps of a ternary compound, aluminum gallium arsenide, you put X equal to 0, then you have pure gallium arsenide. If you put X equal to 1, then this is 0 and you have aluminum arsenide. That represents the two ends here. X equal to 0 is gallium arsenide. X equal to 1 is aluminum arsenide. Gallium arsenide has a direct band gap of 1.42 eV. So direct band gap, I mean at the gamma point, and it has an indirect band gap of 1.9 eV. There is a minimum at 1.9 eV as well, but it's indirect. But the material is direct band gap, or if a material has, whether a material is a direct band gap material or an indirect band gap material is determined by which one of them is smaller. And therefore, gallium arsenide is a direct band gap material because its direct gap is 1.42 eV, smaller than the indirect gap minimum. And similarly, aluminum arsenide, the indirect band gap at 2.16 eV is smaller compared to its direct gap at gamma point, that is 3.02 eV. And we call aluminum arsenide an indirect band gap material. Now, what you see is, as you change from X equal to 0 to X equal to 1, the direct band gap represented by the solid line varies from 1.42 to 3.02. In other words, by changing X, you can modify the direct band gap or the band gap of the material. That's one of the most important reasons why we go for ternary compounds and quaternary compounds. There are many other reasons. All right. So let me come to semiconductor Pn junction devices in optoelectronics. The light emitting diode, which is a simple forward biased Pn junction. A laser diode is also a forward biased Pn junction, but with certain conditions, which I will explain now. And a photodetector is usually a reverse biased Pn junction. All right, let me start with semiconductor lasers. The invention was in 1962, almost simultaneously by 4 different groups. There are a large number of advantages. Each point can be explained for several minutes. So it's compact, efficient, the possibility of direct modulation, and of course, optoelectronic integration, integrating several components on a single chip. Compact, we know the size of semiconductor lasers is much smaller compared to the size of a typical helium neon laser that we use in the laboratory. And it's efficient. The efficiencies we are talking of anywhere from 20% to 60% wall plug efficiency. That is optical power divided by electrical power fed can be very, very high. Just to understand the numbers, if you take a helium neon laser or an Nd:YAG laser, the efficiencies are less than 1%. All right, let me go to the basic structure. The basic structure is a forward biased Pn junction. And here are typical dimensions which are shown. The chip length is typically about 300 micron, and the height here could be about 100 micron. And it is made in a direct band gap material such as gallium arsenide or indium phosphide. So if you look at the basic construction of the material here, so what is shown is the chip, a semiconductor laser chip. The yellow part here is the metal which is deposited at the top and the bottom. You start with probably a N-doped substrate and deposit active layer, then a P-dope. This is a simple structure. There could be many more layers here for various technological reasons, but this is a simple structure of a laser diode, and light comes out from here. This is one of the end phases. So if I show you the longitudinal cross section, a section from here along this line, then the section would look like this. And this is the active region, and these are the outside cladding regions, and then the metal contacts in its simplest form. So the metal electrode is for current injection, and we need to have doped material to have a minimum electrical resistance. So this is the longitudinal cross section of a laser. And what you notice, so you have a thin layer of gallium arsenide, which is sandwiched between 2 other layers on the outside, which is of aluminum gallium arsenide. Aluminum gallium arsenide, as we just saw, has a band gap which is higher than the gallium arsenide. And therefore, this is called a heterostructure. A heterostructure Fabry-Perot laser. Fabry-Perot laser because the reflections come from the 2 ends, cleaved ends of the laser chip. And therefore, it's called heterostructure Fabry-Perot laser. The laser, as we know, comprises of a gain medium and a resonator. That's a cross-section of a simple Fabry-Perot laser. Now, for those of you who are not familiar with the heterostructures and heterojunction, heterojunction simply refers to junction between dissimilar semiconductors. So, for example, gallium arsenide and aluminum gallium arsenide. Unlike you have P silicon and N silicon, which is called a Homo junction, here the materials are different, and therefore the junction here is called heterojunction. And a double heterostructure laser, which is the normal laser structure, comprises of a thin layer of a low band gap material such as gallium arsenide sandwiched between 2 layers of higher band gap material. This forms a double heterostructure. Why we go for double heterostructure? Let's see. So this is the Nobel Prize in 2000. Nobel Prize in Physics was awarded for developing semiconductor heterostructures used in high-speed devices and optoelectronics. So Alfaro and co-workers proposed the double heterostructure laser in 1970. All right, let me not go into those details. Now, just to look at the points, why heterostructure? The advantages, there are a large number of advantages. I have listed some of them. Most important ones are carrier confinement, optical confinement, lower absorption losses, and design flexibility, etc., etc., etc. So I will just pick up one or 2 points. Now, this is a Homo junction device, as I already mentioned, junction between identical materials, gallium arsenide p-doped and n-doped. This is a Homo junction. So if you see the energy band diagram of a Pn junction, which I'm sure you are familiar, this is before contact, p-type material, so Fermi level is here, n-type material, so Fermi level is here. In the conduction band, there are plenty of electrons here and plenty of holes here. Now, if you make a junction, the energy band diagram of the Pn junction looks like this. Okay, this is the junction region, which in electronics we call the depletion region. Now, if you, and there is a built-in voltage which comes up. Now, if you forward bias, then you are supplying more potential energy to this end. Therefore, this end starts going upward related to this end. And therefore, this is the new energy band diagram. So what has happened is, note that before contact, after contact, but before applying forward bias, we have one Fermi level all along the device. But when you forward bias, you are pushing the material into what is called as quasi-equilibrium. And in quasi-equilibrium, there are two Fermi levels in this active region or the junction region. The two Fermi levels are ECF, one for the conduction band and one for the valence band. And these are called the quasi-Fermi levels. Now, note that when you forward bias, typically the width of the depletion region or the active region is 1 to 2 micrometer, depending, of course, on the doping concentrations P and N. Now, let's go to the, just do not have to bother about the mathematics, but the point is the carrier concentration is given in terms of the Fermi energy here, EF, and for N and P. In thermal equilibrium, we have this familiar equation, which all of you may be knowing, that which is called law of mass action, that is N into P is equal to Ni square. But if you push the semiconductor into quasi-equilibrium, there are two Fermi levels now, EFC and EFV, and therefore N into P, the product is Ni square into e to the power EFC minus EFV by kT. Or now N into P is greater than Ni square if EFC minus EFV is positive. So if you increase the separation between quasi-Fermi levels, the carrier concentrations can become very large. This is the main physics point in forward biasing a double heterostructure. So here is the double heterostructure energy band diagram before contact, before they are making contact. There's a P side, N side, and a thin layer of low band gap material. When you make contact, the energy band diagram gets modified like this. So why these kings, etc., I will not go into this. You can always see detailed lectures on this. But the point is, when you forward bias, note that before you forward bias, there is one Fermi level even here. But when you forward bias, then there is a separation between the Fermi levels. And more important thing to note is, because of the potential barrier here and barrier here for holes, the holes are confined to this region and electrons are confined to this region. They cannot go over to the other side because of this barrier, potential barrier. This is, please see this energy, potential energy, and therefore this is the potential energy barrier, which means the carriers are forced to stay together in the same space. And this thickness, which you have chosen, is D of the order of 0.1 micrometer. This is not 1 to 2 micrometer as in the case of a Homo junction medium. Now in the heterojunction, because you have chosen the thickness of this intermediate layer, you have confined the carriers to a small region in space, thereby increasing the carrier concentration, which determines the gain in the medium. That is called carrier confinement. Second important point is optical confinement. This is quite simple because for a given material system, it so happens that low band gap material has a higher refractive index and a high band gap material like aluminum gallium arsenide has lower refractive index for a given material system. And therefore, what you have here is a refractive index profile which is like this: high index, low index. And therefore, you have an optical waveguide which supports a mode of propagation. So here, if you look at this structure, this is low index outside and high index here. Therefore, light gets trapped in this layer by total internal reflection in simple terms. And what is shown is a mode profile. So light propagates back and forth, confined by the refractive index here. And that's called optical confinement. This also helps very much, as we will see in the theory. All right, so there are many advantages as I mentioned, but let me go over. And therefore, finally, the standard structure of a laser diode, a simple laser diode, is this. This is a double heterostructure laser. Now, this curve you would have, this graph you would have seen in earlier lectures. What is shown is lattice constant versus band gap energy, a very important graph for fabrication engineers, because when you fabricate, for example, look at this gallium arsenide and aluminum arsenide are along the vertical line here, which means they have almost the same lattice constant, which means they are lattice matched. Therefore, any ternary compound aluminum gallium arsenide which lies on this line will be lattice matched to gallium arsenide. This is a very important requirement in optoelectronics, because in optoelectronic devices, we cannot tolerate defects. Defects are detrimental to the performance of the device, and therefore lattice matching is very crucial unless you are going for strained layer epitaxy. Similarly, here itself, I would like you to see that the substrate indium phosphide is lattice matched to a compound here with the red dot, that is indium gallium arsenide. The composition is indium 0.53 gallium arsenide. This is a material, as we will see, is widely used for photodetectors. So again, coming back, so here is the laser structure, and I go to the characteristics of a laser. So the operating wavelength today, semiconductor lasers can be easily found anywhere in this range, 0.4 micrometer to 1.7 micrometer. Of course, there are special lasers which can go beyond this. The materials, typical materials used for the blue-green region here, 0.4 to maybe up to 0.6 is InGaN gallium nitride. You would have heard about these material systems earlier. And 0.6 to 0.78 indium aluminum gallium arsenide and gallium arsenide. And this is the most widely used laser in this range. 0.78 to 0.88 micrometer is based on gallium arsenide, most widely used for all commercial applications. And indium gallium arsenide phosphide, the quaternary compound on indium phosphide in this range. All the communication, optical communication lasers are made by this in the 1.55 micrometer window. So what is shown here, of course, per element, per device, typically we can get laser outputs anywhere from 1 milliwatt to 1 watt. Today, single elements emitting at 1 watt are easily available. The important characteristic which is shown here is current, forward current through the diode versus optical power. So you note that up to a threshold current, the output is very little, and then beyond the threshold, the output increases almost linearly and rapidly. So this is the threshold current. So threshold current is a property specific to laser diodes and not for light emitting diodes. So this is a specific property. There is a threshold beyond which the output power increases rapidly. But also a very important point to note is if the temperature of the device increases, then the threshold moves to higher values and the output power drops. You can see the slope also changing and the output power would drop. The temperature dependence is very critical for laser diodes. So what is shown here is the spectrum of a laser diode below threshold. That is when it is below threshold in this region. So you are increasing the current here, let's say 10 milliampere, 20 milliampere, 30 milliampere, and so on. And then you see that the power increases slowly like this. So this is the spontaneous emission spectrum because it is still below threshold and stimulated emission is not at dominating. And this is the spectrum over a very wide range. You can see literally 100 nanometers, 7,500 to 8,500 angstroms. And when the laser goes over about threshold, then what you see, the same output, it is the same output changes into this form. So what it shows are the longitudinal modes of the laser. These are the resonance frequencies of the resonator, which are building up here inside the laser cavity. This is because of the cavity. These are the longitudinal modes. So then I added a real picture, which I had taken just last month from our lab. So what is shown is the longitudinal modes on a spectrum analyzer. So you can see the longitudinal modes. This axis is wavelength. You may not be able to read it. It is about 1541. You can see the mean wavelength is 1541 nanometer. And the width is just 3 nanometer. Total width is 3 nanometer from here to here. But if you pick up only one longitudinal mode, that is, if you consider a laser which emits only one longitudinal mode, then the line width will be extremely narrow. It will be extremely monochromatic, highly monochromatic. And that they are called single frequency lasers. And one of the designs which is used is a distributed feedback laser, widely used in optical fiber communication. So this is a design where you have, it's the same double hetero structure, but there is a frequency selective grating in the cladding, which selects or which provides feedback at only one wavelength satisfying the Bragg condition. And this is called, that's why it's called a distributed feedback. There is no reflection coming from the ends because the ends are anti-reflection coated. The reflection is coming from the grating as the mode propagates along the active layer. So if you see the spectrum on a, so this is schematic, of course, that you will get for a DFB laser, the output spectrum will comprise of only one longitudinal mode, but a normal Fabry-Perot laser will comprise of large number of longitudinal modes. A very important, okay, so this is the laser diode package. I'm just showing from a particular company here, just to say that, yes, these are the DFB lasers. And you can see that these are gigabit components for telecom trunk applications. And the package which is shown here is called a butterfly package. You can see the leads, unlike normal electronic ICs, where the leads go down into the board. So here leads are coming to the sides like a butterfly wing, and hence it's called butterfly package. There's a reason for this, that you need access to the belly of the chip to cool the device very efficiently. That's why the leads come outside. So what I have shown here is a photograph from some of the devices in our lab. So this is a DFB package, which is fiber pigtail. This is an optical fiber. Of course, it is broken. That's why I'm showing. So this is a butterfly package, and this is the TO packages. So typical laser diodes which you have in CD players. Actually, this laser diode is from Sharp Corporation, giving 25 milliwatt of laser output, and other devices which I have shown here. So they would look, these are called TO cans, and this is called butterfly package. An exotic design is a vertical cavity surface emitting laser. I will not go into the discussion here into this, but it has two reflecting stacks here, and the output comes vertically up from the chip, not from the sides like the normal Fabry-Perot laser. The advantage is you can have a very dense array of such devices on a single chip. The second point you see here is the active layer normally comprises of multiple quantum wells. So I will just touch upon this quantum well and proceed further. recall that the double heterostructure has a thin layer sandwiched between two high band gap layers. So if you plot the energy band diagram in the depth direction like this, so you have higher band gap, that is this layer, and you have lower band gap, that is the colored layer, active layer here, and again higher band gap. And if you see the refractive index in the depth direction, it does this like a optical waveguide, and light is confined. So some numbers are shown here. Now, if you rotate this through 90 degree, what you see is this structure. I rotated that. So this is the thin layer, which is of low band gap material, gallium arsenide. You can see 1.42 eV, and the outside is aluminum gallium arsenide, 1.78 eV. And I have shown certain numbers here, but what you have is a quantum well. This is a potential well. It's not a quantum well yet. So formation of a potential well and barrier in the energy band diagram of a laser. So this is the double heterostructure laser rotated through 90 degrees, and you have this energy band diagram. Why we have shown like this? Because we identify, physicists identify this as a potential well, because this is potential energy axis. There is a potential well. And now, when will this become a quantum well? So if you calculate, the diagram is a little light, but these are actual calculations which one of my students had done. So when the thickness is 100 nanometer, that's about 0.1 nanometer, 0.1 micrometer, it supports large number of energy levels. So these are the eigenstates of the potential well. If you reduce this dimension of the well to 20 nanometer, then you see now it supports less number of eigenstates, that is allowed solutions. And if you reduce it further down to 4 nanometer, that is 40 angstrom, you can see that it supports just two, one state here and one state here. There is a discretization of the energy levels, or we call this as quantum size effect. So for D, the thickness of the well less than or of the order of de Broglie wavelength, the potential well goes over to a quantum well, or the double heterostructure goes over to a quantum well structure. So there is the quantum well laser, where you have discrete energy levels and electrons from this energy level combining with holes here in this discrete energy level, giving out photon. There are lots of interesting material about this quantum well structure, but I will not go into that. I have shown this because this, we reduce the thickness in one direction. If you reduce the thickness in the other transverse direction, then what you will get is a quantum wire laser. Why I am mentioning this is, in the next talk, Professor Jagdish is going to discuss quite a bit on quantum wire laser, because they have done a lot of work in this area. All right. So one last point about quantum wells is the multiple quantum well structures. What is an MQW structure? It is an array of non-interacting identical quantum wells, but non-interacting. The field, this is the wave function of this potential well. This is one potential well, second well, third well. The wave function here goes down to 0, and there is no overlap of the wave functions between the wells. There's 0 here, and therefore they are non-interacting identical wells. Then why do we use such structures? We use structures to enhance the properties of a single quantum well and effectively increasing the volume of the material. And what do I mean by that? You can see now. So this is a multiple quantum well laser, which has two. In this, only 2 quantum wells are there. There can be, usually there are about 4 or 5 quantum wells which are used. By using more quantum wells, which are non-interacting, you are making use of the quantum size effect, but the volume of the material is increased. Unless you have sufficient volume of the material to generate light, the output power will be very little. So by using MQW, you can increase, for example, the output power from a laser. So multiple quantum well lasers. One last point with quantum wells, that is, if you have a quantum well and if you apply an electric field, the potential energy variation becomes like this. This is the potential well. Now, if you apply electric field, the potential energy changes. And the field, which is the wave function here, which is perfectly symmetric, starts becoming asymmetric. If you apply stronger fields, so you can see here, the field shifts, the wave function shifts, and you start getting oscillatory solutions here. And the wave function can leak through the barrier. And this is an important effect called quantum confined Stark effect. That is, the change in the energy level, the change in the energy eigenvalues, which is called Stark effect, in a quantum confined structure like potential quantum well is called quantum confined Stark effect. This is the basis of realizing quantum well modulators or electroabsorption modulators. But I will not go into those details. So let me come very quickly to the light emitting diodes. So light emitting diodes are forward biased PN junction diodes, which all of us know. And what determines the color of an LED or a laser diode for that matter? It is the energy band gap of the semiconductor material. So to realize red, orange, yellow LEDs, normally aluminum, gallium, indium phosphide is one of the materials which is used. Whereas to realize blue LEDs, it is based on blue and green LEDs are based on indium gallium nitride LEDs. So a slight change in the composition of the alloy changes the emission wavelength of the LED. Now, this is the energy band, the band gap versus lattice constant diagram. So we don't have to go into any of the details, but just see that gallium nitride is here. The band gap is about 3.3 or 3.4 eV, and the corresponding band gap wavelength is here. And therefore, indium gallium nitride, that is InGaN, this line represents the ternary compound indium gallium nitride. So by changing the composition, you can have material which are emitting easily in this range 0.4 to 0.6 micrometer. In principle, you can go to even longer wavelengths, but there are certain technological reasons we have better materials here. So usually from 0.4 to 0.5 or 0.55, one uses InGaN as the widely used material for blue and blue-green lasers. All right, I come to white LEDs. There are two ways of realizing white LEDs. One, a combination of red, green, and blue. You can have a combination and then a proper mixture of these will appear white. The other and more popular one now is using a blue LED to excite a phosphor, an InGaN LED to excite a phosphor which emits a broadband white light. It's a broadband light which we call white light. It's really not like the sunlight which goes from 0.2 to 2 micrometer and beyond. It doesn't go that much, but it is almost white in the visible region. And that is what we have for all the lighting applications. So you can see the various applications. All these diagrams are easily available in internet sources, and you can see them: automobile lighting, swimming pool lighting. And I wanted to show, this is the IIT Delhi campus. All the street lights now we have are using white light LEDs. The campus is lit by white light LEDs. We don't have any more mercury lamps and sodium lamps which consume a lot of power. And the 2014 Nobel Prize in Physics was given to these gentlemen for the invention of, the citation reads, for the invention of efficient blue light emitting diodes, which has enabled bright and energy saving white light sources. I come to the last part, that is semiconductor photodetectors. So the basic idea is it's a reverse biased PN junction. And if you see the energy band diagram, an incident photon creates an electron hole pair which is swept apart by the built-in potential at the junction. And that leads to, so if you connect this P and N to a wire in the external circuit, there will be a current flow. And the mechanism, but today the diodes which are used are pin structures. So there is a question, why pin structure? So if you see a diode, this is still a diode, it's not a pin. This is the actual junction between P and N. And in the region 1 and 1 here, it is the depletion region or the active region where there is a built-in potential. There is a field, electric field variation. And therefore, any photon which is incident and creates an electron-hole pair will be swept to the two sides by the electric field present. And therefore, you have a current in the external circuit. The light which is incident far away from the junction does not see any electric field. And therefore, the electron-hole pairs which are created are not being drifted by any field. And therefore, they could be loitering around and may recombine without contributing to the current in the external circuit. And that means only the region close to the junction is important from the point of view of photocurrent generation. But this region is just 1 to 2 micrometer wide. And how to increase this region? And that led us to pin diodes, where you have highly doped P and N at the two ends and an intrinsic region which is all over, extending from one end to the other end. And you see, because it's an intrinsic region, the electric field variation, if you plot, of course, you have to see the lecture, the video lectures to see how you get such electric field, etc. But the electric field variation will be like this, which means all over this I region, there is an electric field. And therefore, anywhere an electron-hole pair created will be drifted to the two ends and contributing to the current. Therefore, there are many advantages here of high speed, high frequency response. In a sense, today all detectors used are pin photodetectors. The practical structures, the way we study in the class, like a PN structure like this is good for explaining only, but no practical structure is like this. In a practical structure, you have to start from a substrate and then deposit layers. So you start from a substrate, for example, here, and deposit layers like this. And what you see, for example, let me pick this structure. There is an indium phosphide substrate you start with. This has a band gap of 1.35 eV. And you deposit an indium gallium arsenide layer. I mentioned to you that this is perfectly lattice matched to this. And therefore, this has a band gap of about 0.74 eV. And this is the material which is used for 1.3 to 1.6 micrometer range. This is one of the best detectors. So you have a layer of indium gallium arsenide deposited, and then a high doped small thin layer of P plus to make a contact with the metal here. You have to form good ohmic contacts. And that's why you have always you will see that the last layer before the metal contact is a P plus and a N plus. That is to form good ohmic contacts. Now, the point I am making is photodetectors are also double heterostructures. That's the only objective in showing all of this. Okay? And as I mentioned earlier, this indium gallium arsenide is lattice matched to indium phosphide. Finally, I want to show that there are other materials, particularly this material, cadmium telluride and mercury telluride here, have almost similar lattice constant, almost on the vertical line. And therefore, mercury cadmium telluride was a material and is a material which is widely used for this wavelength range. See that this is the infrared. The defense people always have used these mercury cadmium telluride in the near infrared. It's a very good detector which is used widely for the near IR. Some characteristic parameters of the detectors, I will not go into the detail, but just that quantum efficiency is one of the important parameters. And quantum efficiency determines the photocurrent IP generated, which is proportional to the optical power incident, and the proportionality constant is called the responsivity. So you can see the responsivity R, because this is a parameter which is given in the data sheets of all photodetectors. They will always give you this number, responsivity, typically 0.5 amperes per watt. So responsivity is IP photocurrent to the optical power which is incident. And this responsivity is a function of wavelength, as you can see here. And eta, the quantum efficiency, is also a function of wavelength. Therefore, what is important when you use a detector, when you plan to use a detector, is to see its spectral response. That is responsivity versus wavelength. And you see this is an important graph which you will see in all detector data sheets. If you are using a silicon detector, note that the responsivity is very good over a wavelength range of approximately 0.4 to 1.1 eV. And the responsivity is very nice because the silicon band gap is 1.1 eV, and therefore at around 1.1 micrometer, the responsivity goes down to 0. Beyond that, it is transparent. Therefore, if you are operating in the 1.55 micrometer band, the detector to be used is indium gallium arsenide. Wonderful detector here with very high responsivity in this range. And here I have listed some materials, silicon, germanium, InGas, which are the widely used materials for photodetectors, and the wavelength range, the peak responsivity, and here is the graph. The graph speaks. So if your application is in this region, silicon will not work. But if your application is in the visible region or near IR here, then silicon is a wonderful detector. So I come to the summary here that semiconductor double heterostructure is a versatile platform for optoelectronic devices. All the devices that I discussed are double heterostructures. Laser diodes, light emitting diodes, photodetectors, electroabsorption modulators, and so on. And therefore, fabrication of the double heterostructures and all the fabrication related issues which you have heard in the last few days is very, very important. The materials, the lattice matching, and other fabrication methods, because all the devices are double heterostructures. Simplest ones. Of course, there are more exotic devices which need additional processing. One last slide which I want to show is some of you, if you are interested, how to pursue this area. Of course, all of you have crossed this 12th standard, so you are in BSc or MSc or BTech or wherever. But if you start from here, let's say for your children, some of your children may be here, then there are two ways to pursue this area. One way is you go to a BTech program, electrical, electronics, ECE, engineering physics. Then you could do an MTech in applied optics, optoelectronics, optical communication, laser technology. There are various MTechs available in the country. And then you could pursue a PhD. You could go over to industrial R&D or academics and other R&D organizations. If you have missed this track, then there is no harm. You can go through the other track. You do BSc, then go over to MSc, and then again you have these channels open. Either you can go via MTech or you can go directly to PhD. So I thought I will show this slide for all of you, those of you who are interested. And
really good, sir. Really good. Really good.
Thank you very much.
Thank
So I stopped on time.
Yeah. Thank you, sir. Thank you very much. Sir, will you take few questions? Few questions?
Yes.
Niklesh,
Okay,
if there
sir.
is any question, you just...
Yes, sir. So there are a few questions. First question is from
Okay, please.
Banumati. Does the QCSE generate non-linear oscillation which could be helpful for non-linear optical devices?
Normally, QCSE is used for linear applications, but there is a non-linearity indeed, because it linearly does not with the applied electric field, the shift does not increase linearly. Initially, it increases linearly, but subsequently, it does not. And therefore, there is a nonlinearity there in terms of the energy shift. But primarily, it is used for making use of the linear property of shifting of the absorption edge of the semiconductor.
Oh, okay, sir. So next question is from Saima. Why photodetectors are reverse bias, whereas lasers and LEDs are forward bias? I think that's a basic.
I think I discussed that. You reverse bias it because you want to sweep the generated carriers. So if you reverse bias it, the carriers are swept in opposite direction, electrons and holes, because photodetection is a reverse current generation, whereas LED and laser diodes are forward biased, which means the holes and electrons move towards each other and recombine in the junction region. And that recombination gives rise to the generation of photons. So it's a reverse process.
Okay, sir. Sir, next question is from Arjunan. How to form depletion region? Simply connect P and N junction means automatically form the depletion layer.
Yes, whenever there is a PN, of course, this is quite elementary. I'm sure you have studied this in electronics. Whenever you make a PN junction, because of the difference in carrier concentration on both the sides, there is a migration of charge carriers across the junction. When the charge carriers migrate across the junction, you leave behind immobile ions on both the sides, and that leads to a built-in potential.
So I guess what Arjunan wants to ask is like how do we like attach the PN junctions? So there are a few techniques.
No. PN junctions are not attached. Please remember, when we say it is contact, it is not normal contact. They are called metallurgic contacts. So it's not making contact, because physical contact will not make a PN junction.
Yeah.
So you have to really have metallurgic contact, or you have to deposit one over the other, material one over the other. And then only it will form proper PN contact.
Yes, sir. I guess that was what he was asking. So next question is from S. Selvamani. So while reducing the thickness of active layer, does it necessary to consider quantum tunneling phenomena, or we neglect it?
No. The quantum, when you reduce the active thickness of the active layer further, then quantum size effects come into play automatically, because you see, this is the potential well that we see. If you calculate this, unfortunately it's not, it's a bit light, but these are actual calculations of with the actual numbers. You can see that when I had taken 100 nanometer as the width of the potential well, the number of solutions supported by this well, solution to the Schrodinger equation. You solve the particle in the potential well problem for using the Schrodinger equation, and that gives you these eigenvalues. And they are very large. As you reduce, the number of allowed solutions go on reducing, because the allowed solutions have to satisfy boundary conditions. And that's why it's the boundary condition which decides how many solutions can you have in a given structure. So reduce the dimension, then the boundary condition will be satisfied by lesser number of eigenvalues. And similarly, reduce further, there are only 2 eigenvalues. Is that okay?
Thank you, sir. Thank you. Yes. Professor Shenoy, thank you very much. Thank you very much. Sir, thank you for joining us. Thank you, sir.
Sir,
Professor Jagdish is waiting. Professor Jagdish is waiting.
Okay, sir. Okay, sir.
So
we'll be in touch with you, sir.
Yeah. So do I?
Sir, yeah. Please.
Shall I unshare?
Yes, sir.
Yeah, Duraksha.
Thank you, respected sir. It was an honor to hear such a useful talk from a valuable personality like you. Thank you. We are highly indebted to you. Thank you.
Thank you. My pleasure.
Thank you.
Now, starting
Thank you.
with our last session for day 5th, I would like to introduce our next speaker, Professor Jagdish. Professor Jagdish is a distinguished professor and head of Semiconductor Optoelectronics and Nanotechnology Group in the Research of Physics, Australian National University. He is currently serving as past president of Photonics Society. He has published more than 950 research papers, including 680 journal papers, and holds 5 US patents. He has received many awards, including IEEE Pioneer Award in Nanotechnology, IEEE Photonics Society Engineering Achievement Award, OSA Nick Hall in York Junior Award, IUMRS Somia Award, and UNESCO Medal. He has received Australia's highest civilian honor, Companion of the Order of Australia, for his contribution to physics and engineering, and in particular nanotechnology. Now, I would request Professor Jagdish to kindly start with his session. Over to you, sir.
Okay, thank you very much for that kind introduction, And so basically, it's great to join all of you on this important short course on semiconductor physics and technologies. And I would like to thank Dr. Shah for inviting me to participate in this wonderful session. And I also want to thank my good friend, Professor Shenoy, for introducing to you about the optoelectronic devices and the fundamentals. So that really allows me to be able to go into the next stage of advanced stage of talking about some of the research developments which are taking place and in the use of semiconductor nanostructures for a wide variety of applications. And I hope you're able to see my slides and there are no major issues there. And so
yes, sir. Yes, sir.
That's good.
No,
very good.
Yes, sir.
Very
Yes.
good. Okay. Thank you. So it has been mentioned that I have, I'm a professor at the ANU, but also have honorary appointments in various parts of the world, including India, Japan, China, Taiwan, US, UK. It's really a pleasure to work with my colleagues in various parts of the world. The beauty of science is that there are no national boundaries. We can all work together. And that also makes the science much more interesting and exciting as well. So really, before I proceed further, I would like to thank my collaborators, and the talk which I'm giving today is a collaborative effort between my group at the Australian National University and many groups in Australia, US, UK, China, and Sweden, Italy, Russia, Switzerland.
If you want to go fast, go to it.
So I want to thank all of them and all the professors in those universities and also all the students and postdoctoral fellows, those who really contributed to our joint research. And without their hard work and commitment, there's really nothing much to talk about. And so this is my group at the Australian National University. And in fact, this is about 10 to 12 nationalities at any one time, and then very bright young people. And so, in fact, Anha Bhatt, she comes from that part of the India, and I don't know exactly whether what is the city she comes from, but I've forgotten. She told me, but I've forgotten. But certainly, she comes from that part of India. So really, we got a student from that part of India as well. So I also want to take this opportunity to thank our funding agencies for supporting our research and allowing us to have fun. And as you know that if they stop giving us money, then we cannot have fun, which is not good for us, right? Science is always fun. So that's why I do science for fun. So here is an overview of my talk, and I'll give you the motivation why we're interested in nanostructures and then a wide variety of optoelectronic devices. And then I'll tell you about how do we grow these nanowires and nanostructures. And then I talk about nanowire lasers and LEDs and terahertz detectors. And I'll not have time to talk about terahertz modulators, but I'll talk about nanowire solar cells and using nanowires for photoelectrochemical water splitting and using nanowires for neuron growth, and I'll draw some conclusions. Before I proceed further, I would like to thank many groups, those who are working in the field of semiconductor nanowires and nanostructures in various parts of the world. And really, we all learn from each other. The knowledge has been built based on others' contributions, and it's important in science for us to acknowledge other groups, those who are working in our fields, and I want to thank all of them to enriching our field for their contributions as well. So before I proceed talk about semiconductor nanostructures, let me back off a bit and let us talk about industrial revolutions. So all of us are aware that the first industrial revolution has started with the steam power and mechanization. And second industrial revolution started with electrical power and mass production. And third industrial revolution started with computer power and automation. And people are predicting the fourth industrial revolution is going to be bringing the biological world and the digital world together. And light is going to play an important role because we get a lot of information, about 80 to 90% of the information to light to sense and interface humans and machines, for example. Okay. So that means, the fourth industrial revolution, people are predicting that, biological world and essentially human machine interaction and interfacing will be much more enhanced in the future. But also light-based technologies are currently about 1 trillion Australian dollars, and people are predicting by 2030 they will be about double that amount of the industry activity, indicating that the light-based technologies are going to play an important role in the next generation of the fourth industrial revolution, for example. So the World Economic Forum in 2018 has identified the technologies needed for the future. They've identified the holographic displays coming out of our phones, for example, and wearable optical sensors, and then where they're monitoring your health and be able to report to your doctor as and when your health condition is changing. And also light navigation and communications, like a LiDAR technology, and also 3D vision and gesture recognition, and enhanced machine vision and augmented reality. All these technologies required miniaturized and smart optical systems. And then, in fact, we are working as part of a center of excellence funded by the Australian Research Council. So in this center of excellence in active meta-optics, and we are trying to generate light using nanostructures, and then manipulating light using meta-optics, and then detecting light using nanostructures. And this center has been led by my colleague, Professor Dragomir Neshev. And so we've got about 5 different universities participating within Australia, about 20 other universities in various parts of the world. Really, our aim is to be able to really create something like a flat lenses and a range of other technologies, which are really going to play an important role for the next 7 years or so. And again, our center is advertising for some postdoctoral fellowships and PhD fellowships. And please keep an eye on it and then see whenever the advertisement comes out, apply for it if you're interested in working in this particular area. So now let me talk about optoelectronics. So of course, Professor Shenoy has already spoken about optoelectronics and optoelectronic devices. It's wonderful to really hear such a learned professor giving the talk and then introducing you to the subject. As essentially, optoelectronics is conversion of electricity into light by using LEDs and lasers, for example, and conversion of light into electricity using photodetectors and solar cells, for example. So really, it's a matter of converting light into electricity or conversion of light into electricity into light. Okay. As all of you know that the silicon is a workhorse for the microelectronics industry. But unfortunately, silicon is not a very good light emitter. And because it's an indirect band gap semiconductor. I'm sure that some of the previous speakers might have told you about that. But in order to get a good light emission, you need to have a direct band gap semiconductors. That's where we focus on group 3-5 semiconductors, group 3 of the periodic table, and group 5 of the periodic table of gallium nitride, indium nitride, gallium phosphide, gallium arsenide, gallium antimonide, aluminum antimonide, indium antimonide, and a combination of these materials. These different materials have got different band gaps. The energy difference between the bottom of the conduction band and then the maximum of the valence band, for example. So depending on what color of the light you want to really generate from an LED or a laser, or what color of light you want to detect, and then use a combination of these materials in order to be able to do that. For example, the gallium nitride technology, combination of gallium nitride, aluminum nitride, indium nitride, has led to the development of the blue LED, which was a missing link for up to 20 years back or so, where we had the red LEDs and green LEDs, but there was no blue LED. So the development of these particular nitride-based technologies, 2014 Physics Nobel Prize has been awarded to these Japanese scientists, Dr. Amano, Dr. Akasaki, and Dr. Nakamura. And of course, the same materials which are used for LEDs can also be used for making lasers, for example. And we and other groups are really working in this particular area. Today, of course, the development of this LED technology led to large area displays, for example, and where it's in the time square here, the bright light, and that even during under sunlight, bright sunlight, you can able to see the TV because of the fact that these LEDs are extremely bright and LED displays also. We're also using them for lighting applications, like LED lights are very common now. And in fact, we are not allowed to use incandescent Edison lamps nowadays in Australia because of their very inefficient light emission process also. Today, I'm able to talk to you today by using internet. So what is the backbone of internet? Optical fiber communications. So the signals from my computer are translated into optical signals using lasers, and these signals are transmitted to the optical fiber. And on the other end, these optical signals are detected using photodetectors. They're converting the optical signals into electrical signals, and that's why from there you're able to listen to me today, for example. So really, the optical fiber communications play an important role. And then these are operating at the 1.3, 1.55 micron wavelength region. That's because those are the wavelengths at which the optical fibers have got the lowest absorption and dispersion. So that's why people end up doing these ones. So we work on lasers and photodetectors used in these optical communication systems. And they are made out of, again, indium gallium arsenide phosphide combination of these materials in order to be able to emit light in infrared region of the spectrum, or they detect the light, for example. Also, same materials could also be used for making infrared detectors, which are used in the biomedical imaging applications, or night vision applications, or even looking at the manufacturing, where, for example, if you want to look at the way the heat is generated in a computer chip while you're operating the computer chip, and then be able to identify where the heat is generated, and you can redesign the computer chip so that you can really dissipate the heat efficiently. Also, same materials are used for making highly efficient solar cells. For example, there is something called a multi-junction solar cell. So you can stack different materials and be able to absorb the different parts of the solar spectrum. And then nowadays, the efficiency of these solar cells is more than 47%, for example. So unfortunately, these solar cells are very expensive because of the fact that they're expensive materials which we're dealing with. But these solar cells have been developed for the space applications where the satellite cost is so high. You wanted to have the most efficient solar cells so that the satellites will be lasting and doing their work for a longer period of time. But once if the 40% efficiency has been exceeded, people started thinking about how can we use it for terrestrial applications. So people have been developing something called a concentrated photovoltaic systems, where you got a light concentrator, where it is using these parabolic mirrors, and then you really concentrate the light at this focal point. And then because the concentrator system cost is so high, you want to have the most efficient solar cells. That's where the 3-5 compound semiconductor solar cells have been explored for this particular application also. Okay. So now let me move towards nanowires. Why we're interested in nanowires? So nanowires are seen as building blocks for the electronics and photonics. So one of the unique things with the nanowires is that, the lattice mismatches are no longer an issue. So whenever you are depositing two-dimensional materials, thin films, for example, you always have to worry about what is the lattice constant of the material which you're depositing, what is the lattice constant of the substrate which you're depositing, lattice constant of the unit cell which repeats itself in a crystal, for example. Okay? So because of their nanostructure and three-dimensional nature, this material which got a large lattice constant with respect to a substrate, it can expand without creating any defects or dislocations, and it can contract if the material has got a smaller lattice constant without creating dislocations or defects. So really, in principle, you should be able to grow nanowires of any material on any substrate. For example, people have been dreaming about bringing the 3-5 semiconductor optoelectronics with the silicon microelectronics together, but the lattice mismatch has been a real problem, and always the defects have really played an important role there. But if you use in the nanowire form, you can, in principle, be able to do that. You can also make axial heterostructures. Professor Shenoy has just spoken about quantum wells. Say, for example, if we grow these materials, for example, the red material is different than the green material. By really putting a very thin material of this green material, you can really create a quantum confinement, and you can create quantum wells within these nanowires, for example. You can also dope these nanowires to Pn junctions. One part of the nanowire is P-type. Another part of the nanowire is N-type, for example. In the gap, you can put quantum wells, for example, if you want to really do that, for example, for making LEDs and lasers and other things, which I'll come back and then talk. You can also make radial heterostructures nanowires, like the red material is different than this pink material or so. So that means you can be able to create a multi-core shell nanowires and other things. Again, you can create a core shell quantum structures and other things, again, which I will come back and talk about. And then you can also create the branch nanowires. And that means it really opens up a lot of opportunities for us. So here are some of the examples which I'm giving you from my own group. You can see that we have shown that we can grow gallium antimonide on top of gallium arsenide nanowires. Despite large lattice mismatch, we're able to show that you can make atomically perfect nanowires. You can also make indium arsenide nanowires on top of gallium arsenide. You can create these branch nanowires so that they can be used as cantilevers and scanning probes and things like that. You can also make indium phosphide nanotrees here. I'm giving an example where these nanotrees are absorbing different parts of the solar spectrum. They're very good for energy harvesting applications. Then also we have been really moving from nanowires into nanomembranes, and then be able to explore and then see what else we can do. Most importantly, International Technology Roadmap for Semiconductors, the Semiconductor Industry Association, these are the people who are identifying what technologies are needed for the next generation electronics. They've identified nanowires as a key technology component for electronics. In fact, IBM Zurich recently has demonstrated indium gallium arsenide nanowire transistors on silicon 6-inch silicon wafers, indicating that these 3-5 semiconductors can also be very good not only for optoelectronics, but also for electronics applications as well. It is looking extremely promising. Okay? Nanowires are used for making LEDs, lasers, photodetectors, biosensors, and solar cells, which I'll come back and then I'll share with you some of the examples which we have developed in our own laboratory. If the nanowires are so much of importance, how do you make these ones? So really, there are two main techniques which we use. One is called as a VLS growth process using some metal catalysts. Another technique is called selective epitaxy. In this case of metal, we also use something called MOCVD, metal organic chemical vapor deposition. There's an alternative technique called a molecular beam epitaxy. You can use either of the techniques which you want to use. And then we happen to have MOCVD reactors at ANU. And particularly MOCVD is a technique which is used by industry for manufacturing a wide variety of optoelectronic devices like lasers and other things. So that's why we've chosen MOCVD for our research, for example. So in this case, what we do is that we take a gallium arsenide wafer, put some gold nanoparticles of, say, for example, 50 nanometer gold nanoparticles. For example, you can buy this colloidal solution. You can put a droplet of this colloidal solution onto this gallium arsenide substrate. Gold has got a melting temperature of more than 1000 degrees Celsius, but once the gold starts reacting with the gallium or indium or aluminum, what happens is that the alloy temperature of gold gallium or gold indium or gold aluminum temperature, melting temperature comes down to as small as 350 degrees Celsius. So now if I take this wafer with the gold nanoparticles of gallium, gallium arsenide wafer, put into the MOCVD reactor, heat it up to somewhere between 370 to 500 degrees Celsius, and then you're really creating this eutectic liquid of gold gallium, for example, and then you introduce the gases needed for the growth of gallium arsenide, for example, here, and then trimethyl gallium and arsine. These gases get incorporated in this liquid alloy. It gets supersaturated. Crystal starts precipitating out. Gold is always sitting on the top. You can see the electron microscope image of this 50 nanometer gallium arsenide nanowires. You can see the transmission electron microscope image of this particular structure. You can see this dark spot is a gold nanoparticle. And then here's the gallium arsenide nanowire, which is absolutely atomically perfect. This is the work of Dr. Hannah Joyce. And then during her PhD, she demonstrated these atomically perfect, cylindrically shaped nanowires, developing something called a true temperature growth process. We start the growth at a high temperature, and then afterwards, after nucleation, we reduce the growth temperature so that you can get very good uniform structures also. So now Hannah Joyce is now an associate professor at Cambridge University in UK. So we also can make these nanowires as small as 20 nanometers and as big as 300 nanometers using this so-called VLS growth process and the VLS, vapor liquid solid growth mechanism. And vapor is getting incorporated to a liquid, and we're getting a solid. And this is Wagner and Ellis and Bell Labs have called this technique is called as VLS growth process. In the case of the alternative technique called selective epitaxy, in this case, we don't use any metal nanoparticles. We take an indium phosphide substrate, for example, here I'm giving you here, deposit some silicon dioxide using plasma-enhanced chemical vapor deposition, and put some photoresist, and then put some electron beam lithography system, and then do the right patterns of this particular dots, for example, and then create holes, and then transfer those holes through silicon dioxide so that everywhere else is silicon dioxide is coated, and in the holes, indium phosphide is exposed. Then you put this into a MOCVD reactor, and then heat it to somewhere between 650 to 750 degrees Celsius, introduces the gases needed for the growth of indium phosphide, in this case, of trimethyl indium and phosphine. These gases dissociate at these temperatures, and then they start growing beautiful nanowires here. This is the work of Dr. Qian Gao, who is now an engineer in Blue Glass, a company manufacturing LEDs. So you can see that one, you can see that because she's created these ordered patterns of these holes. So that's why she's able to create these ordered patterns of these nanowires of indium phosphide. You can see the top view of these ones. You can see beautiful hexagonal facets also. And again, of course, we have also used either of the techniques can be used to grow any of these 3-5 semiconductors. Again, using this technique, we made the nanowires as small as 70 nanometers, as big as 700 nanometers. Depending on the applications, you end up going and choosing the right diameter nanowires also, which I'll come back and then share with you on what type of techniques, what size of the nanowires which are using for various applications. We've taken these indium phosphide nanowires, excited them with a laser pulse to generate electron hole pairs, and then we look at the light emission from these structures also. You can see that we estimated the quantum efficiency of the light emission as a function of the excitation laser power density. You can see that you can get quantum efficiencies as high as 50% from these indium phosphide nanowires. This is a red curve. And then we also compared these performance from the nanowires with the epitaxial layers, or the two-dimensional thin film layers of indium phosphide, and the blue curve, and both are showing really very similar quantum efficiency performance, indicating that the surface defects do not play an important role. The broken bonds on the surface of indium phosphide nanowires don't play an important role. In the case of recombination, you end up getting excellent optical properties from these indium phosphide nanowires. So these are very useful for making lasers and so on, and I'll come back and then share some of those results with you. So then we asked ourselves, instead of opening a hole in the silicon dioxide mask, what will happen if we open a slot or a ring? This is work of Dr. Nain Wong, who just finished his PhD. And so what he has done is that he's really deposited silicon dioxide, do electron beam lithography pattern, and put some photoresist, do electron lithography pattern, and created these different patterns also. Again, he spent a lot of time in optimizing the growth conditions of the temperature and then various flow rates and pressure and all these things in order to be able to get some of the best quality nanostructures also. Excuse me. So you can see that when 9 opens up this slot along a particular crystallographic orientation of 101 bar, puts this into an emulsivity reactor, and heat it up to somewhere between 650 to 750 degrees Celsius, and introduce the gases needed for the growth of indium phosphide. Now you can see they can get the beautiful membrane-like structures here. And then because you created a slot, and then the these structures are growing in that particular slot. And with particular these side facets of this particular crystallographic side facets. If you open this slot along another crystallographic orientation of 112 bar, and again he puts it into the emulsivity reactor and heat it up and then grow these structures, you can also create the membranes. But in this case, these membranes are thicker than these ones due to the lateral growth taking place here. And you also end up having the different kinds of facets of this 112 bar zeros. But if you open this slot in between these two directions, you end up creating these beautiful diamond-like structures with these alternating facets of these ones. Now we can see, instead of just making nanowires, we're able to make nano membranes and nano diamonds, and really this opens up a lot of opportunities for us to be able to explore these ones for a wide variety of applications like nano membrane transistors, nano membrane lasers, and a range of other applications we're exploring. And in fact, my collaborators at the University of New South Wales, Adam McLeich's group, has demonstrated some beautiful transistor devices from these particular indium arsenide, particularly nanomembranes also, which I will not have time to talk about. So what will happen if you open a ring, for example? If you open a ring, again, by optimizing the growth conditions, and Nain Wong is able to show that you can get these beautiful ring-like structures with these alternating facets of those structures, which I was telling you earlier. So if you keep on growing further, then this gap gets filled up and you end up creating this nice membrane structure. If you keep on growing, ultimately you end up getting these hexagonal facets because these are the lowest energy crystallographic facets, and crystals always likes to be in the low energy state. So in the process, you get these beautiful hexagonal faceted structures also. So really, this is opening up opportunities for us to really grow wide variety of shapes and wide variety of structures. And by the way, we're using these ring resonators, ring-like structures as ring resonators for making ring resonator lasers also. And this is again, my new student, Wei Wong, has really recently demonstrated ring resonator lasers, which again will not have time to talk. So Nain Wong has taken these structures and then looked at the light emission from these ones. So you take these nanomembranes, nanodiamonds, and nanorings here, and then he excites them with the electron beam using the cathodoluminescence, and then look at the light emission from these ones. You can see a very bright light emission from all these nanostructures, indicating that really we've got a highly uniform structures, and you get no defects, and you get a really excellent light emission from these structures. As I mentioned, that we're using for a wide variety of nonlinear optics applications, lasers, and a wide variety of structures which we're exploring at this stage. So till now, I've only talked about materials. So now let me move towards devices. So I'm sure that Professor Shenoy talked about lasers, and then I'm sure that he mentioned about the gain medium you need to have in a laser, and you need to have a laser cavity, you need to have mirrors, for example, and you need to pump this gain medium so that the gain is larger than the losses in the optical cavity, and lasing starts taking place, for example. So what we say is that model gain need to be equal to the optical losses, then only lasing starts taking place. And then here's a case where this actual equation which says exactly the same thing. The gain need to be equal to the internal absorption or scattering losses in the gain medium, and then the mirror losses which are taking place. Some of the light is leaking out, and that also need to be taken into consideration in this case. Okay? This is an undergraduate optics course. We all studied about lasers, and then population inversion, and then essentially having a laser cavity in order to be able to make lasers to work. So if you take a nanowire of the right dimensions, if you shine light from the top, and then what happens is that these nanowires act like waveguides, and light propagates along this particular nanowire if you choose the right kind of nanowire, for example, and then the both ends of the nanowire act like mirrors because of the fact there's a large refractive index difference between the semiconductor, which is 3.4 in this case, and the air refractive index of 1. So now you can see I don't really have to put mirrors or anything. Each nanowire could act like a laser because these nanowires are direct band gap semiconductor materials like gallium arsenide or indium phosphide, which have already got a gain, and then this act like a waveguide, and both ends of the nanowire act like a mirror. So that means I got a laser cavity and a gain medium. If you pump it, and then it should in principle be able to make these nanowires to act like lasers. So if you get everything right, that's an important one. So we've been working on making a wide variety of nanowire lasers. This is the first nanowire, gallium arsenide nanowire lasers, which I will come back and tell you. Dr. Drew Saxena has demonstrated that one during his PhD. He was now at Imperial College in UK. And then Woodside indium phosphide nanowire lasers have been demonstrated by Qian Gao, who is at Blue Glass. And then we've looked at the quantum well lasers. Again, Professor Shenoy has spoken about quantum wells. Also, Dr. Tim Burgess has demonstrated zinc-doped nanowire, gallium arsenide nanowire lasers. I'll not have time to talk about all of these nanowire lasers. I'm going to share with you one or two examples. So Drew Saxena has gone off and did some simulations. So he looked at a wide variety of optical modes, TM01 mode, T01 mode, HE11 mode, various optical modes, and then looked at how the light is propagating to these nanowires, for example, here. He's looking at the TM01 mode, which has got the highest intensity of the light field at the core of this nanowire, for example, and then propagating through a 260 nanometer gallium arsenide nanowire here, for example. So in fact, Drew Saxena has plotted threshold gain for lasing as a function of the diameter of the nanowire for a nanowire which is about 10 microns long, for example. You can see that the different optical modes have got a different threshold gain for lasing, and typically the lowest threshold gain for lasing is for nanowires which are about 250 to 300 nanometers. So that's why we started using these larger diameter nanowires than smaller diameter nanowires. He also calculated the amount of gain as a function of the injected carrier density. And again, you can see that the threshold-like behavior, like a lasing behavior, and threshold carrier density is dependent on the temperature of the device which you're really operating with. Again, these simulations are playing an important role for us to be able to design and then be able to demonstrate innovative nanowire lasers, for example. So here is a case where, based on Drew Saxena's simulations, Dr. Jenny Jiang and Nain Jiang, who is now at Cambridge University, is designed to grow these gallium arsenide, aluminum gallium arsenide 4-shell nanowires, and then about 6 microns long in this case, transfer them onto a glass slide, and then Drew Saxena has done these measurements. You pump with the laser pulse and look at the light coming out of these ones. You can see a very broad light emission below threshold like a LED, and like essentially spontaneous emission is coming out of this one. Above threshold, you're seeing a very sharp light emission, and they're behaving like lasers, for example, here. So you can also see the output versus the pump intensity. Again, this threshold-like behavior here. And then the log-log plot of the output versus input pump intensity shows the S-type behavior and the narrowing of line width. And also that you can see that these beautiful coherent interference fringes are taking place because of the two coherent dipoles that are emitting from both ends of the nanowire. In fact, Bruce Saxena has simulated for this particular nanowire, and it's matching very well with what's been experimentally measured. And these were the first gallium arsenide nanowire lasers operating at room temperature, which are optically pumped. He published his work about 7 to 8 years back or so. So really, this really created a lot of excitement in the community, those are working with these nanowire lasers. By the way, these nanowires are really, really tiny lasers. And then just to give an idea, and then I can put about 20 lasers within the width of your hair. That really tells you how tiny these lasers are. Why we want to use these tiny lasers? Smaller the laser, they consume less energy, which is important for a green internet, for example. And then also that they can be switched on and off faster, again, faster internet as well. Also for sensing applications and a range of applications people want to use, including using them for cell imaging and things like that. So what, in fact, this is a collaborative work with my colleagues at University of Strathclyde, Professor Martin Dawson, Professor Michael Stein, and Professor Antonio Hurtado. They developed a technique called nanoscale transfer printing technique. So what they can do is that they come with a PDMS stamp, pick up the nanowires, and then drop them wherever you need to drop them. So thereby you can precisely locate these nanowires wherever you want. This again, research fellow Dr. Ben Gulhaber has spent a lot of time in optimizing this particular technique. So here is a case where they've transferred these nanowire lasers onto flexible glass substrates, and you can see these nanowires here, and then they pump them and look at the light emission from these structures. You can see light is coming from the both ends of the nanowire, and all of these nanowires are lasing. Also, you can see nice threshold-like behavior. This part is acting like a light-emitting diode. In this part, it's acting like a laser. Also, very sharp light emission because of the resonances, and that's what you would expect from a laser, for example. So now you can see that we can precisely be able to locate these ones and wherever you want. Also, it's a very gentle process as well. So they've transferred these ones onto polymer materials, for example. Here is a case where the polymer waveguides, SU8 waveguides, they created a Y junction, and where they've located 2 nanowire lasers in the front of this Y junction, and then couple the light through this Y junction, for example. For multiplexing and demultiplexing applications, you want to get multiple signals passing through an optical fiber. You need to have some sort of a multiplexer. You can make use of these ones, for example, here. So they were able to show that you can get a good light propagation, and then they're really very comfortable, very good for example, polymer optoelectronics applications, for example. And this student, Dimitar Geotics, has really done this work. So then I asked them, can you locate these nanowire lasers into nano antennas? So here is a case where there's a work of Professor Fang Ren. She's now at Nanjing University. She was in my group for some time, and where she was able to show that she was working on these so-called terahertz metamaterials, for example. So in this case, you can see these nano antennas are here, and there is something called is made out of aluminum. There was a gap called, in the middle, there's a gap here, and where we requested them that they'll be able to locate these nanowires in this gap here. So you can see that they're able to locate them very nicely. You can see the close-up of this one. This is a nano antenna. It is a nanowire here. So when you do not have a nano antenna, light is coming from the both ends of the nanowire because nanowire acting like a fabricated cavity. But whereas you got a nano antenna, suddenly light is coming from the vertical direction. So that means you're able to, first of all, instead of having edge-emitting light lasers, we're able to demonstrate vertical emitting lasers or so. Again, threshold-like behavior, and then a sharp light emission. And so really this opens up opportunities, and particularly we're able to make for the first time vertical emitting nanowire lasers. So that means we can make use of these ones to create ordered patterns of these nanowire lasers, which could be used for these holographic display applications, to facial recognition applications, and a range of things which can be able to do that also. And a lot of hard work has been put by many students and postdocs, including Professor Fang Ren at that time. Till now, I've only shown you the nanowire lasers which are optically pumped. So that means I'm pumping one nanowire lasers with another laser. But industry ultimately wants to have electrically injected nanowire lasers because that's where it's more convenient rather than having to find a laser to be able to create another laser, though it has got its own applications. So this is work of Dr. In-Suk Yang. He is now at Samsung in Korea, and he came from Samsung and did PhD with us and gone back. So as Professor Shenoy was mentioning about Pn junctions, you need to really dope this indium phosphide with a P-type dopant, like zinc is used as a P-type dopant for indium phosphide, for example. Then he's grown this indium gallium arsenide quantum well here, for example, this yellow layer. And then he puts N-type indium phosphide on the top here, for example. Again, this growth to optimization took about 2 years. You need to be able to grow optimum conditions with no defects and things. Then he spent a lot of time in these making contacts using electron mimeography, for example. He transferred these nanowires of Pn junctions onto a glass slide and put some gold titanium and then make electron mimeography to be able to make these nice contacts here. You can see the shape of this particular nanowire is looking like very much of a shape of the schematic which I'm showing you here. And then after making contacts, then what In-Suk has done is that he injected current and look at the voltage. And you can see that the IV characteristics is showing like a nice typical diode-like behavior, indicating that his PN junction growth has worked well. Also, his ohmic contacts has been very good in terms of being able to make nice PN junctions here, for example. So now you inject the current into these nanowires and then look at the light emission from these structures. So you can see that as and when you're increasing the amount of current injected into the nanowire, and then you end up getting higher and higher amount of light emission coming from these ones. Also that the light output versus injected current shows not like a threshold, like a lasing behavior like thing, but increase in the power is taking place, but still it's not behaving like a laser. It's essentially behaving like an LED, nanowire light emitting diode, which is essentially nothing but a spontaneous emission because you don't see any line with narrowing or anything of that sort. You see a very broad light emission, for example. Yeah. So essentially, this is, again, by the way, there are 2 peaks. Again, these 2 peaks are dependent on the quantum well, which is forming on the top of the nanowire here, which is an axial quantum well. There's another quantum well is forming on the side of the nanowire, which is so-called core shell nanowire or core shell quantum well or radial quantum well. And then depending on which one quantum well is emitting, that end up having 2 different emission peaks. This is from the axial quantum well, and then this is from the radial quantum well, because they got different thicknesses and compositions, for example. So why we are not able to make electrical injected nanowire lasers? They're only behaving light emitting diodes. The problem is that whenever you put metals have got a huge optical losses. So that means they create a lossy cavity. You have to pump them harder. If you pump them harder, you're generating a lot of heat. If you increase the heat, the gain of the gain medium goes down. You have to pump it even harder to be able to make it to laze. It becomes like a vicious circle. So now we got a new student, Nikita Kagrani from IIT Kharagpur, and she has been spending a lot of time and trying to really replace these metals with other materials like indium tin oxide and other conducting materials, but not as conducting as metals. So thereby we still can be able to inject the current, but not creating too much optical losses or so. It's been a really challenging problem. She has been working on this for the last 3 years or so. We still were not able to demonstrate in a laser, and I'm hopeful that by end of this year or so, we'll be able to demonstrate an electrical injected nanowire laser, which is very interesting for a wide variety of applications. Again, the smaller the laser, and then more efficient they are, and also they consume less energy, and you can switch them on faster, modulate them faster. That means you can use it for faster communication. So before In-Suk finished his PhD, and then he has gone off and then tried to create these nanowire arrays, fill these with the polymer material like a BCB, and then really selectively etch this only polymer to expose the tips of the nanowires, put some indium tin oxide contacts, and put some metal on the top, and then the bottom another metal, so that you can inject current into these nanowire LEDs and look at the light emission. You can see the IV characteristics showing like a diode-like behavior. Again, higher the amount of current, and you can see the higher the amount of light coming out of these ones. In fact, you can see under the probe, there's a bright light emission coming of these ones. And because we are embedding these nanowires in our material, in principle, you can peel these things off for flexible display applications. Like, for example, Samsung and Apple are interested in flexible phones and foldable computers, things. And that's where people are interested in developing these sorts of flexible LED displays for a wide variety of applications, for example. So till now, I've talked about nanowire, the lasers and LEDs. Now let me move towards terahertz radiation. What is terahertz radiation? So in the case of terahertz radiation, we all know about electronics. We talk about microwaves and radio frequency, RF electronics, and millimeter waves. But whereas in the case of light, we're talking about UV light and visible light and infrared light. There was a gap called terahertz gap for many years, and only during the last 20 plus years or so, people have been able to make compact terahertz sources and detectors, for example. We and many other groups are working in this area. So why people are interested in terahertz radiation? It turns out that the many chemical molecules have got fingerprints in the terahertz parts of the electromagnetic spectrum. So for example, here's a case of lactose, monohydrate, and hydrate or so. Also that many of the metals are reflected by terahertz radiation is reflected by metals. So that means in the airports these days, they use terahertz monitoring, not X-rays, because X-rays are ionizing radiation. They create a lot of damage to your DNA. But by using non-ionizing X-ray, ionizing radiation like terahertz sources, terahertz emitters, and then you're able to really look at whether people are carrying any knives or guns or anything of that sort, for example. Also, terahertz radiation can be used for looking at the biomedical imaging applications, particularly cavities in the teeth. They can be useful for wireless communications, where you can download movies and other things onto your smart device. Also, terahertz radiation could be used for determining the water content in leaves. Just to remind you that 1 terahertz is about 300 microns in wavelength. So it's like a 0.3 millimeters, for example, of the wavelength of the light, which is we're talking about here. So again, this is a joint work with my colleagues at Oxford University, Professor Michael Johnston and Professor Laura Hertz. And then there's the work of my student, Dr. Kun Pang, who is now a postdoc at Oxford University. So during her PhD at the ANU, she has taken the gallium arsenide and indium phosphide nanowires, transformed them into a quartz substrate, and made some contacts using electron beam lithography, for example. So then she shines these nanowires with a laser. That means you're generating photo carriers, and then the electric next sends a terahertz pulse. Electric field of the terahertz pulse is the one which separates these carriers, and then in the process you end up measuring photocurrent as a function of time. You can see the time scales which we're dealing with is picoseconds. So really, lifetime of the material really plays an important role. Also, once if you measure the current as a function of time, you can also measure the electric field as a function of time as well. So that means you get the full information about the amplitude and then the phase of the terahertz pulse which has been sent there as well, and including polarization state as well, which I will come back. So to cut the long story short, and Dr. Kun Pang has, during her PhD at the ANU, she has demonstrated this gallium arsenide nanowire terahertz detectors operating at room temperature, and indium phosphide terahertz nanowire detectors operating at room temperature as well. So during her postdoc at Oxford University, she has focused on making these polarization resolved terahertz detectors. So you can see that in this case, she creates the 2 sets of these bow tie antennas and then try to put these nanowires in orthogonal direction of 90 degrees to each other. You can see the close-up of this one. You can see she was using 2 independent nanowires, but one is in one direction and another is in the direction. The challenge has been that avoiding the contact between the top nanowires and the bottom nanowires, and that's where she spent a lot of time in optimizing the conditions in order to be able to really do that one, for example. Again, after 3 years, and then we were able to really demonstrate excellent polarization sensitive, phase and amplitude sensitive terahertz detectors. So what she's using these terahertz detectors are for looking at metamaterials. I mentioned to you terahertz metamaterials where you can manipulate light. And so she designed a terahertz metamaterials, fabricated these ones, and then sends a terahertz pulse through this particular terahertz metamaterial and look at the light coming out of that side. Because terahertz metamaterials, if the light is interacting with terahertz metamaterials, what happens? It changes the phase and the amplitude and things like that. So here is a case where the transmission, you can see, it shows that the X polarization should have this type of transmission, and then Y polarization should have this type of transmission for these particular terahertz metamaterials. And then she has measured using our polarization sensitive terahertz detectors, and again, X polarization and Y polarization. So really, you can be able to use these ones and be able to compare theoretical predictions with experimental work. Is very interesting from the point of view using them for, you can get the amplitude, phase, and polarization state of the terahertz pulse. That means you can extract all the useful information from these structures, for example. In fact, this paper we published last year in Science. So again, 3 years of hard work of Kunpang has really paid off from that point. So now let me move towards solar cells. So again, I'm sure that Professor Shenoy might have spoken about solar cells. And all of us have studied about in a solar cell, you need to have a Pn junction. You need to make the thickness of these layers such that you're able to absorb all the sunlight here. And then the carriers need to migrate long distances to the metal contacts at the top and the bottom. But it turns out, if you take a nanowire and then you make the nanowire as long as you want to absorb all the sunlight, and then you make a Pn junction, which is lateral Pn junction or a core cell Pn junction, that means carriers don't need to migrate long distances. You're able to collect them much more efficiently. For the first time, you're able to decouple the light absorption pathways and carrier collection pathways. But also these nanowires act like light funnels because they've got a high refractive index with respect to the air surrounding it. That means light likes to be in the high refractive index medium, for example. But also that they act like they've got also low reflection losses, so that you don't need to put any anti-reflection coatings or anything. That's all. So again, we've done a lot of simulations. This is essentially electromagnetic simulations of the finest difference time domain simulations of the carrier generation profile. For example, here is a case where we're looking at what should be the height of the nanowire, what should be the diameter of the nanowire, what should be the distance between the nanowires, sort of thing, pitch, for example. So you can see that the most of the current is generated at the tip of the nanowire, indicating that you do not need to make a long nanowires. Even 1 or 2 micron long nanowires are more than sufficient for you to be able to use it for a variety of applications, for example. Again, we looked at the diameter of the nanowire. The diameter of the nanowire should be somewhere between 140 to 160 nanometers or so. And the diameter to pitch ratio should be around 0.5 or 0.6 or so. Again, these plots really indicates and they act like a guide for us in order to be able to really choose the right kind of nanowire source. So based on these simulations, we've grown some of these gallium arsenide, aluminum gallium arsenide nanowires, and then really did this polymer filling, selectively etching that one, put some indium tin oxide as a transparent conducting oxide, put some metal at the top and the bottom, and shine light and look at the start measuring the current from these ones. You can see the actual devices, electron microscope images of these ones of the nanowires, and the nanowires embedded in a polymer material with the tips exposed, and then after coating with indium tin oxide so that most of the nanowires are covered. And then we go and then shine light and look at the current generation from these ones. So again, to cut the long story short, and then these are some of the best nanowire solar cells demonstrated to my colleagues at the University of Eindhoven, Professor Ike Barkers, and then Professor Eric Garnett at the FOM Institute in Amol. So you can see that we're able to demonstrate efficiencies as high as 17.8%. So these are some of the best nanowire solar cells, and then showing extremely promising results. They're looking very, very promising, which is really very good. In fact, the competition is fierce in terms of really beating this record of Lund University, and then of course Rico Eckhart's group, and then of course our group and other groups are working in this area. So we've been working with Professor Laura Gertz at Oxford University. Instead of using polymers, how about replacing that polymer, which is only a structural material, with some organic semiconductors, so that you can make use of the best of the both worlds of inorganic and organic semiconductors. And so then we're exploring this one with the hope that we'll be able to demonstrate nanowire flexible solar cells, for example. So now let me move towards the last 2 topics. One is called water splitting. Water splitting, I'm sure that all of you are hearing about the hydrogen economy and the importance of the greenhouse gas emissions really playing an important role in terms of creating huge greenhouse gas emissions and then leading to warming of the planet and other things. And it can lead to a lot of problems for all of us because we all have got only one planet to really live. So that means we really need to come up with non-fossil fuel-based technologies. And here's a case where we are using semiconductors as photoanodes, for example, here. We shine light onto this one, generate electron-hole pairs, and then the holes are coming and oxidizing the water here, and the electrons are going there and then combining with the protons here and reducing the protons into hydrogen here, for example. So really, this is a beautiful technique, and then challenge is that, how to really identify and then create some of the best materials and also stable materials, which has been the major challenge. And again, this work is led by my colleagues, Dr. Ashok Kalturi and Professor Hotan, for example. Here's a case where So me from Michigan University has looked at what materials are ideal for these ones. You can see that the important requirement is that the band gap of the semiconductor is such that, and then these redox potentials of water need to be in the middle of the band gap here. So for example, here is a case where gallium nitride, for example, and it really covers the redox potentials of water because these redox potentials are within the band gap of this is a conduction band of gallium nitride, valence band of gallium nitride here, which covers very well. But the only problem is that gallium nitride is a large band gap material to only absorb the UV light, but not the visible light. Same thing case with titanium oxide, but indium nitride is not really straddling both these redox potentials of water here. So, but if you combine the indium nitride and gallium nitride, you get to indium gallium nitride, which has got the decent band gap where it can absorb some of this visible light. Also, really straddles the redox potentials of water, for example. Again, I borrowed this slide from Professor and me, which I want to thank him for that. So now we've looked at some of these gallium nitride nanopillars and nanorods, and then looked at this electrochemical water splitting and look at the photocurrent density as a function of the over potential of these structures. And you can see that you can go and look at these ones. Gallium nitride is very difficult to normally etch chemically. But under these photocatalysis conditions, photooxidation takes place due to accumulation of holes at the surface. So what we found is that if we deposit some cobalt oxide on top of this one, and then this act like a co-catalyst and also hole scavenger, so in the process, we were able to demonstrate a stable performance from these particular nano electrodes for in the future generation of the hydrogen generation, for example. Most recently, by the way, gallium nitride is not the ideal material. Again, as I mentioned, that it's got a too large a band gap. That means it's not really absorbing the visible light. And then our future direction, let me finish off with the last top, the brain repair. So in this case, and all of us have got about 80 billion neurons. And then this is the work of Dr. Vinny Gautam, who did her PhD from Jawaharlal Nehru Center in Bangalore, now a lecturer in biomedical engineering at University of Melbourne. So because these neurons really form into this neuronal network like this. So whenever you get a brain damage, then what happens is that means you lose some of the functions because you've broken some of these neuronal network. You may not be able to talk or move or eat or some problem or the other. We asked ourselves, can we really create a neural patch and then be able to make these connections back and be able to help people with the brain damage and neurological disorders? So again, Vinny has spent more than 3 years in optimizing various conditions now to be able to make these things to work. And here's a case where she's growing a neuron, and there's a cell body soma here, as these neurites and axons are really following these patterns of this indium phosphide nanowires beautifully here. You can see they're really following these patterns. You can see some of the dendrites are coming from these axons as well. So instead of using a single neuron, what will happen if you get a multiple neurons on the same indium phosphide substrate, nanowire substrate? This square box is the one where you got indium phosphide nanowires, and then outside ones are the ones which is a flat indium phosphide surface. You can see these axons and neurites are really following these beautiful patterns in the square pattern and other things beautifully. Outside this box where you're seeing random connections. So what Vinny does is she does something called a calcium imaging. In this case, she puts a calcium dye. As and when these neurons are firing action potentials, ion channels are opened up, calcium ions are passing through these ion channels, and then the fluorescent intensity of this dye is dependent on the concentration of the calcium ions which are present in that particular medium. So once she does that, once she takes the correlation maps, if this neuron is firing, what's happening to this neuron and this neuron and this neuron and this neuron, and try to create correlation maps taking place in this neural network. She compares these neuron states with the neurons grown on nanowires, so that because most of the neuroscientists use plain glass substrates, for example. So here's a case where she's looking at fluorescence intensity as a function of time, and she looks at a different neurons, 1, 2, 3, 4, 5, and you can see that all these neurons are randomly firing, and there's no correlation, and you see very little correlation coefficient here. But whereas these neurons which are grown on nanowire substrates, you end up having all the neurons firing at the same time, and you can see excellent correlation coefficient, indicating that we're able to really optimize these things and be able to get excellent performance from these ones. Also saying that there's some sort of a synchronized and correlated activities taking place in this neural network. When Vinny Gautam presented his work at a neuroscience conference a couple of years back at Melbourne, they were asking her what neurons she are growing. She said she's using rat neurons, and they said, why are you wasting your time? How about using human stem cells and then use those ones for growing these neurons, for example? So now we got a funding which has been supported by Dementia Australia Research Foundation and the Little Bar Foundation. And then really, we are now working with stem cell biologists, and they are developing the CRISPR technology with Cas9 and be able to really create a patient-specific stem cells from the Alzheimer's patients, for example, and also healthy people. And then my colleagues at University of Wollongong, neurobiologists, they're using these organoids and then with introducing microglia from Monash University and trying to understand the signaling behavior of these neurons which have been from the Alzheimer's patients with healthy people, and then so that you can really learn about what is the differences. And then we're working with computer scientists doing the deep neural networks, analyze the data, and then be able to really use this one for stimulating neurons for to be able to help people. There's a project which is for next 20 years or so, but we only got the funding for 3 years. And working with the neuroscientists, neurobiologists, stem cell biologists, computer scientists, and nanotechnologists, it's really, we're learning quite a lot. It's been great fun. We're also developing some neuroelectrodes, nanoelectrodes for stimulating the neurons as well. With that, in conclusion, nanowires open up opportunities for manipulation of light matter interaction at the nanoscale, developing a new class of lasers and LEDs, Terahertz detectors, integration of optoelectronic devices on various platforms, nanowire solar cells and photoelectrochemical water splitting to generate hydrogen, and engineering the growth of the neural networks also. And finally, I want to leave you with some information. And as I mentioned, that I'm currently serving as the editor-in-chief of the Applied Physics Reviews, which has got impact factor of 17.05. And in fact, we're expecting that this will also increase even further in June this year. We'll learn more next month or so. And again, you got a breakthrough results in research, or otherwise you want to write a high impact original research reviews. Please think of our Applied Physics Reviews. I already mentioned about our Center of Excellence, and then also the PhD students and postdocs. Please keep an eye on this website. And my wife and I have started an endowment to really support students and young physicists coming from the developing countries to come and spend some time at the ANU and really to give something back to the community, because we benefited from my teachers. And I started my life in a very small village in India, studied in front of a kerosene lamp, and I lived with my high school teacher in a neighboring village in order to finish my high school. Without my 2 teachers in the high school, I'd probably be plugging the fields in India. As a gratitude to all of them, we were really trying to support the next generation so that to be able to, we can also open the doors for them, for example. I'll leave you with some information about various charitable work which we do. With that, I'll stop here. I'm happy to answer any questions you may have. Thank you very much.
Thank you, Professor Jagdish. Thank you, Professor Jagdish. Thank you.
Thank you very much.
Thank you.
So there are a lot of questions.
Sure.
So few of them I'll ask.
Thank you. Thank you. I'm happy to answer them. What let me do, get out of this one so thereby I can really focus on their stop sharing. Now let me see. Okay, now I can see the people here as well. So then we can really, I can really listen to them, and I'm happy to answer any questions they may have.
Sure, sir, sure. So first question is from Revanath Sutar. He's asking, sir, can we build an advanced solar cell or panel with help of C60 molecule? Yes, then how? Yes, then how? And if no, then why? Please answer.
Okay. So the C60 molecules are very good for doping the organic semiconductors, which people have been using, but not as layers, because you see the C60 molecules are so small. If I really want to make these things, you need to make a Pn junction, or otherwise you need to have the so-called type 2 band alignment in the organic solar cells. So that's where, you really create a large area. Solar cells is much more difficult, but C60 has been used as a dopant in the organic semiconductors, and people are using for organic solar cells or so. So that's the challenge is it cannot do everything what you want. So that's what you need to always think about. If I want to make a solar cell, what are the components which I need to have? And then what are the best materials I can bring together? And then bringing those together, you'll be able to create the best solar cells possible, for example. Okay. But as you know that most of you know that the organic semiconductors, people have demonstrated 10 to 12% or so, including the dye-sensitized solar cells or so. But then recently, people have all jumped onto these perovskite solar cells, where already more than 23% efficient solar cells have been developed, and they're looking extremely promising. But only problem is they are not stable. All these demonstration of these solar cells is been in the fume hoods, in the controlled ambient of argon ambient or nitrogen ambient or so. The minute you take them out, they start, humidity really kills them or so. So what we are doing with my colleagues at engineering is trying to coat these on with or bury them between the glass slides or so that they have not been exposed to the humidity and air, and so thereby can deliver good performance from those things. So always you need to think about what is the application which I have in mind, what is going to really help me to be able to achieve that goal. And different materials are good for different applications, and you have to choose those ones for those applications, for example. Good question, but it's C60 itself is not sufficient, but it can be a component in the organic solar cells.
Thank you, sir. Sir, next question is from Dr. S. Gananam. Why quantum dot materials are widely used in optoelectronic devices comparatively than quantum wires and wells? It may be size concerned 1 to 10 nanometers only for quantum dots or any other reason. Please explain, sir.
Okay, so in fact, in all honesty, the quantum wells are also heavily used. If you're using, for example, all these internet and other things nowadays, in fact, quantum well lasers, which in fact we were working on these quantum well lasers in 90s and early 2000s or so. Some of the 980 nanometer lasers which we developed, we had a world record output power. They're used for pumping optical fiber amplifiers in the optical fiber communication systems and other things. Quantum well lasers are still used. What is so special about quantum dot lasers? Okay, as Professor Shenoy has mentioned, I'm sure, is we got this quantum wells, you got only the quantum confined in one direction, and the electrons can move around in the 2 dimensions. In the nanowire or the quantum wire, you end up having electrons can only move in one direction. In quantum dots, you're confining carriers in all 3 dimensions. So why people are interested in quantum dots? One of the advantages of quantum dots is that, for example, if I'm making a laser, and because of the fact that number of states which are available because of the quantum confinement within the quantum dots is small, that means I can create the population inversion much more efficiently. So that means my threshold current for making lasers is much, much smaller. Also, because if I'm using these ones, threshold current is small, and the number of carriers which you need to create these lasers is small, that means I can switch these things off faster. Means, faster modulation, because people want to be able to switch the lasers fast in order to be able to communicate faster, for example. That's one example. Another case is that you can use these quantum dots also to do the infrared detection, because you got a 2 confined states, and again you can excite the carriers by observing infrared, using infrared radiation, and be able to collect those carriers so they can be used for infrared detectors. Again, we worked in the quantum dot lasers and quantum dot infrared detectors and quantum dot solar cells as well. And again, quantum dots can really be buried in a normal semiconductor, so the quantum dots can start absorbing the photons, which have got a smaller band gap than the smaller energy than the band gap of this surrounding semiconductor, the matrix you have. So thereby you're able to use that one for absorbing the sub-band gap, photons, in order to be able to get to solar cells based on the quantum dot solar cells as well. Again, depending on now of course also quantum dots can also be used for single photon sources again, because you got a 2 states, the ground state and excited state, and they could be used for single photon sources as well. Depending on the application you have, again, you go in and choose the right kind of quantum structures. Okay? We have been all working on the quantum wells, and we started working in the 90s or so quantum wires, and suddenly quantum dots came, the entire community has gone off and then really focused on quantum dots. There's a lot of excitement, but now people have come back to quantum wires or nanowires and exploring what are their potential sort of thing. And in fact, fortunately, in my group, we worked on all 3 aspects of it, so thereby I'll be able to really tell you which particular technology is better for what application.
Okay. Niklesh, next one.
Yes, sir. Thank you, sir. Sir, next question is from Dr. S. Selvi. Always using gallium arsenide and indium arsenide materials, why not go for other materials? Other materials also have an required band gap. In this way, why not using other materials?
Okay, that's a good question as well. So again, as I was mentioning to you, the lattice mismatch becomes a major issue. For example, I got a large lattice mismatch. For example, I got one substrate or one material, and the other material has got a different lattice constant, for example. When I try to do this one, what happens is that the layer which I'm depositing gets strained, and then if I exceed a certain critical thickness, what happens is that this layer prefers to get back into its original lattice constant. It creates a lot of defects. So if there are defects, then they are useless as far as optoelectronic devices are concerned. because any carriers you're injecting gets captured by the defects rather than emitting light, for example. Okay, so that's why the combination of materials which we are really using need to be really taken into consideration of those ones. Why we are using 3-5 semiconductors? 3-5 semiconductors are stable materials and efficient materials. In fact, people also have worked on, in fact, during my PhD, I was working on cadmium sulfide, cadmium telluride, and other 2,6 materials, for example. But people, in fact, have been developing zinc selenide as a material for making blue LEDs for a long time. But it turned out that zinc selenide, the bond strengths are not sufficient enough when you're really emitting these things, and they are degrading very, very quickly. So again, if I'm using lasers or LEDs or anything, they need to last for a long time. If a material is degrading, then that means I cannot use them for long enough. So that means industry is not interested, for example. So really, you have to choose the right materials. We've also looked at zinc oxide, for example. Zinc oxide is very interesting materials, and people and we and many groups have worked for a long time. But then very difficult to dope the P-type. P-type doping of zinc oxide is very difficult. So that means you cannot make Pn junctions. So you cannot make Pn junctions meet. You cannot use it for solar cells or lasers or LEDs. And so that's where the challenge has been in the case of zinc oxide. If again, you look at the material, what is possible and what is not possible, and where its strengths are and where I can use it, that's where you can go and use that sort of thing. We work on a wide variety of materials.
Okay. Okay, sir. Sir, next question is from Venkatasai. How the PN type material can form in same nanowire?
Okay, good question. So what we do is that, while we are growing the bottom part, for example, in addition to the gallium arsenide or indium phosphide materials, what gases you need, introduce the small amounts of gases of zinc, diethyl zinc, for example. So then this zinc starts getting incorporated along with the indium phosphide growth, for example. Then after growing the P-type structure, then I remove the zinc gas flow anymore, and then I start introducing the gases which are need to do the N-type doping. For example, silane, dilated silane, silicon. Silicon is an N-type dopant in the case of gallium arsenide or indium phosphide, for example. Then the next part, which is while it's growing, it's ends up forming into N-type. So the bottom part has got a P-type, top part has got N-type. Within the nanowire, you created a Pn junction.
Oh, okay, sir. Thank you, sir. Sir, next question is from Neeraj. How we can fabricate nanowires MOSFET?
Okay, good question. So what we typically do is that, in fact, measuring the electrical properties of nanowires is very difficult. And what we end up doing is we take, for example, we create a FET type structure. We take a doped silicon, and then really have got a thermal oxide, and then put some our nanowires on the top, and then use the doped silicon as a backgate, and then be able to deplete the carriers in this one. And that's how we're able to demonstrate nanowire transistors also. Okay.
Oh,
so it is possible to do that one. In fact, that's what other people are also doing that one as well.
Okay, sir. Sir, again, Dr. S. Selvi, what is the quantum efficiency for nanowire lasers?
That's a good question. To be honest with you, we don't know. You asked the question why, I don't know. But the challenge is that these nanowire lasers are really, really tiny lasers. So basically when they're doing these things, and I have to do that one using an optical microscope. And then what I'm seeing from the top is only the scattered light coming from the both ends of the nanowire. As I told you, the light is coming from the both ends of the nanowire. So that means only you're measuring is a scattered light, not the actual full amount of light which is coming from these ones. So that's something now we are developing the techniques in order to be able to really collect the light much more efficiently to an optical fiber or so. In fact, recent developments I was showing you some of these optical waveguides which I was telling you. Then that's the purpose of that one is also to be able to quantify these quantum efficiency of these nanowire lasers as well. But then also you always have to worry about the coupling losses between various parts of this device, waveguides and the nanowire lasers and other things also you need to take into consideration as well. So we don't know at this stage. We're only at this stage we're able to demonstrate that we're able to demonstrate nanowire lasers and using a wide variety of designs. The next step is to be able to really quantify the amount of light coming out of these ones, as well as also the quantum efficiency of these nanowire lasers also.
Oh, thank you, sir. Sir, there are a lot of questions, so I guess I'll
take
just
one. Niklesh, take 1, 2 bus. That's it. Sir is waiting. Director Saab is waiting. No. So many guests are waiting.
No, Niklesh. Yeah, of course you choose because you can see I have no problems of answering as many questions as people have. But of course, if there are other dignitaries who are waiting for the valedictory function, it's not really nice to really make them to wait. We don't want to be polite.
It's all right, sir. It's all right, sir. Take one, sir. Take one or two. Take one or two.
But also, let me tell you this. Let me say this one. My email has been given in my slides. And also, otherwise, simply type Jagdish Australia or Jagdish ANU. You'll find all my website, and then you'll be able to find my email address. And then essentially send me emails. I'm happy to answer any questions you may have, which I'm not able to answer now because of the fact that we were to, dignitaries are waiting. We don't want to really make them to wait for too long, which is not very polite and nice. Yes, please go ahead.
That's all right, sir. Okay. Take two questions, sir. Take two questions. We'll conclude.
Can you, sir, the next question is from Banumati. Can you please say something about the metamaterials and its research?
Okay. So that's a good question. So basically, one of the unique things of the metamaterials is that, by using, essentially metamaterials are nothing resonant structures, nanoscale resonant structures. By arranging these nanoscale resonant structures in a particular pattern, you're able to really manipulate the light. You can manipulate the phase of the light, and then the polarization of the light, and amplitude of the light. And in fact, our center of excellence, which I'm talking about, and then we're really trying to make use of these metamaterials to really be able to manipulate the light using nanostructures and be able to do things which normally you cannot do. For example, using the metamaterials, you can be able to couple the light so that you don't have to have this curved surface like a lens. You can use a flat surfaces. Using these nanostructures, you'll be able to really concentrate the light, for example. So that means you can create a flat lenses and a range of exotic structures we can create, and that's what really focusing on. We got funding for about 7 years or so. I am working with my colleagues in other departments and my own department and other universities as well. It's really an exciting development, really opens up a lot of opportunities of manipulation of light, essentially, using these metamaterials.
Okay, thank you, sir. Sir, one last question. Do we have nanostructures in SiC? I think that's silicon carbide.
Okay, you can also create silicon carbide nanostructures as well, so there's no problem. One of the things is that the silicon carbide is an indirect band gap semiconductor. So that means it's not a very good light emitter. But at the same time, people have created defects, and those defects can act like a single photon sources. So that's what people have been using. The defects in silicon carbide or the dopants in silicon carbide as single photon sources. My colleagues at University of Technology, Sydney, Professor Igor Aharonovich's group, who is also part of our Center of Excellence, and then they're able to use these sorts of defects in silicon carbide as single photon sources. And in fact, most recently, we demonstrated defects or impurities, for example, carbon impurity in hexagonal boron nitride can also act like a single photon sources and other things. In fact, we published that work in Nature Materials last year or so as well. So anyway, there's lots of opportunities there. As you can see that, I feel like a kid in the lolly shop, right? And we're having great fun doing science. And that's what, of course, students and postdocs make that happen as well. So there, I want to thank all of them for their enthusiasm and then a lot of hard work to allowing us to have fun doing science. Thanks again for your for the opportunity, sir, to speak to
I had one question.
Sure,
we have
go ahead.
Nanowires.
The co-host, then I have to. You're the co-host. You're in charge. So go ahead, Nikesh. Yeah.
Thank you, sir. Sir, we have nanowires. So are those wires solid or hollow, the cylinders?
Okay, that's a good point. So basically, what we could do is that at the moment they are solid. Say, for example, I was telling you that we can make these core shell structures, and then what happens is that these carriers can be confined in this quantum well like a tube-like structure. So when you're making these quantum well lasers and other things, in fact, this essentially the gain medium is like a donut, like a tube. And that's when you have to go for T01 mode, which has also got a donut shape, and the gain medium and then the donut shaped mode is overlapping. That's how we're able to really get those nanowires to lasers, all sort of things. So physically, they may be not shallow, but electronically, you can make them as a tube, for example.
Okay, sir. Thank you, sir.
Thank you very much.
There are
Nikesh.
Yes, sir. Yes, sir. Yes, sir.
Yeah, listen, Professor Jagdish, we owe you thanks, formal thanks, sir. So join us for the valedictory. Join us for the valedictory and we'll make it in between, sir.
Okay, sure. Why not? Okay, I'll stay.
Our Honorable Director Saab is also, yeah, please, sir. Our Honorable Director Saab is also
very good afternoon,
saying that you.
Can I ask a small question?
Sure, of course.
Yeah, since I'm not from this field, but I would like to know the economic, viability of like these processes for producing, nanowires and nanotubes and all that, and like what is their impact on the environment?
I think there is some term looks like it, and
it's at NIT. At NIT it is.
Yeah.
So please connect with the lane, sir.
Yeah, can I repeat my question? If it is not clear,
please.
Yes, sir. Please.
I want to know the economic viability of the process of producing nanotubes and nanowires and their impact on the environment.
Thank you.
Okay, that's a very good question. I think a very important question for that question. So first thing is that let me tell you a joke, which before we go on, then tell you the serious answer. So in fact, I think 3 or 4 years back, we were at Jamia Millia Islamia University, and so Professor Islam and they were starting this new center of nanotechnology. And then Professor Sumio Ejima, who really discovered these carbon nanotubes, he was there and I was there, and Dr. Astosh Sharma from DST secretary was there and other things. So then Dr. Ejima said, oh, this year we are celebrating 25th anniversary of discovery of carbon nanotubes. We still haven't made any money out of them, sort of thing. Okay, so anyway, sort of as a joke sort of thing. But of course, seriously speaking, yes, nanostructures could be used. For example, quantum dots, which have been developed by us and many groups, are nowadays, for example, are used as in the communication systems because of the fact that the temperature, the temperature variations are not really having an impact on the wavelength of the light, which is coming out of these ones are threshold current. So that means what happens is that, you don't need to have a cooling systems and other things. So that means, they're much more, it becomes less expensive and also faster devices sort of thing, for example. And quantum dot infrared detectors, which have been developed by us and many groups, are used by NASA, for example. And so in terms of the carbon nanotubes turned out to be a bit more challenging. But nowadays, people are using carbon nanotube electrodes, for example, for the batteries, for example, in China and other places. In fact, they're manufacturing them, for example. Also, carbon nanotubes and some of the other nanowires and others are used for sensing applications. So basically, these technologies, which are more advanced, means they'll take a longer time to see the applications because they really need to be developed much. It takes much longer time, sort of thing. Yeah. But whereas, of course, the technologies which really are not as complex, then they can easily find the applications much more quickly, sort of thing. Depending on what you're really focusing on, they could be useful, sort of thing. Nanowires, and in fact, there are 2 companies have been started by my colleagues at Sweden, and then they have been really using nanowires, LEDs, for example, also nanowire solar cells. The solar cell company didn't do very well, but the the LED company is really drawing a lot of attention. Apparently, recently they also got funding from Google and others as well. So there's already people are really commercializing some of these technologies, for example. So again, people have to really identify. For example, solar cells, they're so cheap. Silicon. I always tell people, if you try to compete with silicon, and it's a suicidal thing, sort of thing, because silicon is so cheap. Technologies have been developed for the last 50 years or so. You should never compete with silicon. You need to find other applications where silicon cannot do. So that's why the light emission devices silicon cannot do. And that's why the 3-5 semiconductors and these nanostructures play an important role. A very important question. To tell you also that my students are manufacturing these LEDs in China, and for few million a month, for example. So really, some of these technologies, for example, if you're using LED lights, already nanostructures have been used, not exactly the nanowires, but then some of these quantum structures and other things have already been used in the commercial world.
Okay. Thank you. Thank you. Thank you.
Thank you. Very good question. Thank you.
Thank you, sir. Now I would request Duraksha. Duraksha.
Yes, sir. Thank you. Thank you. Thank you, respected sir. We are highly obliged to you. Thank you for the informative talk. As the day is coming to an end, I solely believe we all have learned while enjoying. Starting from session 1st to 10th, we have come a long way. Right from session 1, the talk by Professor J. Kumar on semiconductor crystals for technological applications, wherein he enlightened us about how important semiconductor industry is. He talked about multifunctional devices and discussed how new materials for semiconductors, spintronics. Then Professor Haneni in session 2, wherein he discussed how important quantum mechanics is for electronics and discussed about creating heterostructures by epitaxial growth. And in session 3rd, Professor Jinesh talked about electronic neurons for artificial intelligence. That was really so beautiful. And he talked about evolution in memory technology. Then session 4th, we were enlightened by Dr. Rajendra Singh. He talked about basics of, like, he started with the basics of semiconductors. He talked about four probe method. He discussed about transmission line model. He talked about Schottky model. All of that was really informative. Session 5th was graced by Professor Kanji Lal. He talked about frontier applications of low dimensional semiconductors. The way he explained that total wave function consists of spatial part and a spin part. That was an interesting point. And he explained two-level electron wave function, oxygen vacancies in filament formation. Then Professor Sajad in his session 6th, he discussed a novel way to enhance Moore's law, and he talked about short channel effects. And then session 7th by Professor Rajesh Sharma, he started with the basics of thermodynamics, and he talked about a binary phase diagram, causal model of a crystal surface, seeded crystal growth, all of it. And finally, to our last day, final day, session 8 was graced by Professor Shenoy. The way he explained quantum well with applied electric field was really beautiful. And the way he said that what determines the color of LEDs was really new to me, matlab personally. And then finally, Professor Jagdish in session 9, he talked about optoelectronics and how nanowires act as building blocks for electronics and photonics. He talked about terahertz radiation, all of it. And the important thing that I personally liked was why we need nanowires for solar cells. Well, I must say we really have come a long way. I must say it was so much of the nano wisdom. It feels so good to learn from the eminent people of a field and think that someday we can also reach to the stars like them. And then there goes this, popular saying, for there is always light if we are brave enough to see it, only if we are brave enough to be it. And I would like to thank our speakers who honored us with such valuable information. We are highly obliged and grateful to you all for such amazing sessions. All through these sessions, we were hooked our screens because all of the speakers made it so interesting every day. And every day, like, our chat box used to be filled with all kinds of praises for the speakers, for their lectures. So from a whole team of Srinagar, from all the peers, patrons, our conveyor of the program, our HOD, everybody related to this program, we owe to all our speakers gratitude from everybody. So a big thank you to all of you, really. So now we'd like to start with our session, validatory session. And as you all know, we have a dynamic personality in our department, the conveyor of this program and coordinator, Shah sir. I would like to, you to kindly grace us on this last day. So over to you.
Thank you, Daraksha. Daraksha, thank you. Daraksha, thank you. Yes, I was waiting for this phase. Yes, Daraksha, I was waiting for this phase.
Okay, so thank you to you, sir.
Daraksha,
Yes, sir.
yeah. It's to me. But I'm waiting for Professor Zarabi Saab's video to come up.
Oh, okay, sir.
Yeah. We wanted to see him.
Okay, sir. So I would like to request Professor Zarabi sir to kindly speak a word so that we can just move
No, no,
forward.
no, not no word. This one video is not, his video is not joining. Let's
So
Okay.
he has joined with his
Yes.
video, I guess.
Yeah, he's there, sir.
Yeah, he
He's
has
there.
joined. Professor Shah,
he's there.
yeah, I'm able to see him now. He's there.
Yes.
Okay. I am not in a position to see him. Okay.
So you can
Yes,
change the
I
layout to grid.
huh?
So you can change the layout to grid.
Layout to grid. Grid. Okay. Now it's go. Again, gone. Anyway, Sir Zarabi Saab, am I allowed to,
Yeah,
sir?
please go
We
ahead.
start, please.
Yes.
Sahil Saab, shall we go ahead?
Please go ahead.
Thank you. Bismillahir Rahmanir Rahim. Honorable Chairman, Board of Governors, National Institute of Technology, Srinagar, Dr. M.J. Zarabi. Sir, we have another title for you, a special title, Hardil Aziz. उसे हम काबिल मोहब्बत भी कहते हैं. Professor M.J. Zarabi is lovable and Hardil Aziz in NIT Srinagar. Honorable Director, National Institute of Technology, Srinagar, Professor Rakesh Sehgal, distinguished professor and outstanding scientist, son of soil, probably have joined, Professor R.K. Bhan, Dean Alumni, National Institute of Technology, Srinagar, Professor M.S. Mir, Head Department of Mechanical Engineering, Professor Nazir Ahmed, Registrar, National Institute of Technology, Srinagar, Professor S.K. Bukhari, former Dean, Faculty of Engineering, Kashmir University, now at SSM College of Engineering, Professor Nazir Ahmed Shah, Professor Shenoy from IIT Delhi, Professor Jagdish, Head of Department of Physics, Professor Prince, Professor Wab, Professor Ikram, faculty members of National Institute of Technology, Srinagar, faculty members of the various universities of the country and abroad, friends and dear students. On behalf of National Institute of Technology, Srinagar, and on my personal behalf as a convener of this program, I extend my warm greetings to all. Honorable guests, dear students, being the brain of this program, I'll repeat, short-term course on semiconductors and smart devices was exclusively designed for the students and scholars of the country with an objective to infuse and inject the bliss of semiconductor science at an early age. The age when the mind is pure, when it is inquisitive, when it is unadulterated, and which is proper for the cultivation of knowledge seeds. Dear students, science uncovers the relationship between things, and when we get it right, it allows predictions of the future and permits technological interventions that can change things in a favorable direction. I'll explain it more. Wait. I'll give an example, live example. We have one of the meteorologists in Kashmir. Oh, Professor Bhan has joined. Professor Bhan, thank you. We have one of the meteorologists in Kashmir. He gives the news about the weather. Sonam Lotus. Sonam Lotus makes predictions. Where villages say that Sonam Lotus is connected with the God. It's not like that, dear students. It is he has learned the science behind the meteorology, and he now makes the predictions. I'll quote another example. Medicine and Professor Ali John sound synonymous in Kashmiri context. With barely a stethoscope, and a simple thermometer as a diagnostic tool, he would pick up what others elude from clinical examinations. The reason was that his everything was medicine, and his students are witness to this, that whenever they would visit him, Dr. John used to be engrossed in his studies in his hospital chambers. So when you are in the science, you can make predictions. आप पेशेंट गोया करना शुरू कर दोगे. That is the time that you have learned things. The moment you start making predictions. That's why I have said you that science uncovers the relationship between things, and when we get right, it allows predictions of the future and permits technological interventions that can change things in a favorable direction. Pursuit of science is embedded in man's infinite curiosity to know and understand the secrets of nature. It's up to you, dear students, to take full advantage of such noble initiatives. Our challenges are new. The instruments with which we meet them are indeed new. But the values upon which success depends is a hard work, is honesty, curiosity, courage, tolerance, and loyalty. These things are very old, but these things are true today in this technological world. Before I leave, I'll quote Iqbal, I ahle nazar, zoke nazar खूब है, जो शय की हकीकत को न समझे वो नजर ही क्या. This is Iqbal saying that the spirit of curious inquiry, inquisitiveness, introspection, and analysis will make you to lead not only in sciences but in all walks of life. Thank you very much, sir. Thank you. Before I leave, if there might be lapses or anything that goes to me because I might have done it, I seek pardon from all. Thank you very much, sir. Thank you very much. Darakshan, over to you.
Thank you so much, sir. It was really beautiful to hear words of wisdom from you. So next, I would, it's like it's said that determination and dedication is important to reap the best of all. So this is what speaks of this our short-term course, right? We all did this together and we made it success. So like cheers to everyone. So now next, I would like to request our HOD sir, Prince sir, to kindly speak some words about this course if sir is there. Prince sir.
He was in.
I'm
Dr.
really
Prince.
thankful.
Prince,
Am I audible?
yes, sir. Now you are audible.
Okay. Respected Professor Dr. Ravi Sahgal, Director of our Institute, and all great dignitaries who have joined us in this valedictory function. So I'm highly thankful for the participants, for the speakers. Speakers have been wonderful. It was a great learning experience, and particularly some of the sessions were mind-blowing. And in fact, our students might highly be benefited because the way I see, the Professor Shah had made all possible arrangements, and he was the main player behind inviting all the people on the same platform, and entire nation, almost everywhere from every part of our country, students joined this wonderful short-term course. And I'm highly thankful to Director Sir for all of us encouraging us for such activities. And I wish all the best for our participants, guests, our speakers, and our dignitaries. Thank you very much.
Thank you, Prince. Thank you.
Thank you so much, sir. Thank you for your valuable time. Thank you. Really. Now that we would, this course is incomplete, I guess, without the feedback. So we have like some participants over here. They want to share their feedback about this short-term course. So we have one of the student, Dr. Ariful Islam. He is from Islamic University of Science and Technology. If you could please unmute yourself and say something about, this course, please.
Daraksha, I would like to correct you. He's not a student. He's a participant and he's a
Oh, okay.
teacher.
Faculty.
Okay.
The faculty. Okay.
Professor Arif sir. Arif sir, do we have?
Arif was in. Anybody next one can say?
Okay, sir.
Okay, then
Anyone can say. Anyone
yeah,
can say.
and then we have Miss Parvati. She's from Kerala. Are you there? Please speak something about.
Parvati, you are unmuted.
Hello?
Yeah, Parvati, we can hear you.
Okay. We have much to be thankful to the PG Department of Physics and NITS Srinagar, who conducted this short-term course in collaboration with the Semiconductor Society of India. These 5 days, I attended this session with the same enthusiasm. It's a really informative and helpful and session for me, and I am sure about it will really help me in future also. And the sessions given by all resource persons are very much informative and extremely useful. The words are not adequate to praise their speakers. And I think this is an association of all enthusiastic physicists under the same umbrella to know more about the semiconductors and smart devices and automotives. And it cover all the area from fundamentals to all future applications, from fundamentals of semiconductors and to artificial intelligence and evolution in memory technology and all areas in these 5 days. And I am looking forward to more sessions like this. Thank you for this wonderful session. That's all.
Thank you.
Thank you, Parvati.
Next one.
Thank you. We have Dr. Ariful Islam with us from IUST. Can you speak something, sir?
Arif.
You have to unmute him, I guess.
Yeah, I have unmuted.
Arif, sir, are you there?
Okay, next one. Darshan, next one. Next one.
Then we have Abhishek Ramdas. He's from Pune. Kindly say, is he there? Abhishek?
Abhishek Bhabkar. Abhishek Bhabkar, you are unmuted.
Okay, then we'll move forward. We have Sabah Tabassum.
Next we have with us Basit Iqbal.
Okay.
बस अनम्यूट कर लो इनको.
Basit.
Hello, can you hear me?
Yeah, Basit, please.
So it was a very wonderful experience in this course. We will remain thankful to the all organizers of this course. First of all, I would like to thank Dr. Shah and other organizers for giving us an opportunity to take benefit from an international-like community. I'm very, very grateful and obliged to Dr. Shah for this. I would like to mention some topics which touched my heart and was very inspirational and made me feel the depth and the importance of semiconductor physics. First of all, I would like to mention Sajade Lone. He talked about short channel effects. Dr. R.K. Sharma talked about phase equilibrium of semiconductor materials. And M.R. Shenoy talked about double heterostructure lasers. Mohammad Hannani talked about high electron mobility transistors. Professor Jinesh talked about forming an artificial neuron. Dr. Rajendra Singh talked about Hall effects and the geometry of the measurements. And Dr. Alok Kanjira talked about oxygen vacancy by energetic ions. And lastly, Dr. Jagdish talked about growth of nanowires and nanostructures, nanowire lasers and LEDs, optical fibers, neuron growth. These were topics which were very inspirational and made me feel the depth and the importance of the semiconductor physics. Finally, I would like to thank all the organizers for organizing this course and the speakers for letting us take the benefit from their own research work. It was very beneficial for all the participants. Thank you very much to all of you.
Thank you, Basit. Sir, I have asked from the participants itself. One we have Surajit AGT. Surajit, Surajita. Surajita, can you speak? Hello, Surajita. Sir, I think they have some connection issue.
Okay. Go ahead.
Okay.
Go ahead.
Okay, sir.
Go ahead.
Daraksha.
Okay, so now we can clearly predict because every day our chat box used to be filled with lots of praises for the session. So participants were highly, so now we'd like to, move forward. So I would request we have, Dean of SSM College with us, Professor Anisha, to kindly speak a word. Do we have
Professor Shah.
Professor Anisha, Dean SSM College?
He was with us. Okay, next one. Okay, next one. Go ahead.
Okay, we have a distinguished personality with us, an honored guest. He's from Defense Institute of Defense, Professor R.K. Ban. So please kindly say some words.
Professor R.K. Ban. Welcome, sir. Welcome, Ban Saab.
Am I audible?
Yes, sir.
I'm audible. Okay.
Yes, sir.
Okay. So first of all, I want to thank Professor Shah for giving me the opportunity to say a few words about this course on semiconductors, physics, devices, and automation, and students have gone through. Yeah, I would like to speak on the importance of semiconductor for every and particularly for our country, India. And I would like to give the example of semiconductor kill switch China link and India relevance, which is very much relevant and a hot topic today. Why semiconductor is important for survival of any country? I would like to give the example in our own region, that's India, China. See, post-independent India fought about 6 wars. What is the agenda? What was the agenda? Agenda is there an economic agenda? India is a complex state with a complex country with many huge borders, and we don't have friendly neighbors, very well, China, Pak, and things like that. And currently we know, I'm giving this background, what is the semiconductor link? Ultimately, it all boils down to a semiconductor supremacy. So, we know that we are in conflict with China currently in the central Himachal, Uttarakhand, and biggest is in the Arunachal Pradesh, many sectors. Now, and China also has its own conflicts with, Taiwan, Hong Kong, Vietnam, and all other, about 17 countries in that region around its sea. It's all about economies, and that's all related to semiconductors. I would like to slightly give more insight into that. Just give me 5 minutes. The countries which rules the sea will rule the world. Example is UK. UK ruled most of the world in earlier times, including our own country. So now China is trying to have this supremacy in the sea for controlling the trade. And they want this. They want to be technology power. using semiconductors. And particularly, there's an important field in the semiconductors which is evolving in this respect, that is development of kill switch technology. So I will just give some briefs about it because time is not there. It will need a full-fledged lecture. In its current sea route for the China, it's via Sri Lanka. And in any war, if China wants to sustain for 16 or 17 days, they want oil. And oil has to come through all this long sea route. And that's why everybody knows they have invested huge in that CPC corridor, making a land route via Gilgit-Baltistan to Gavdarport in Balochistan. And it will possibly cut that sea route from 13,000 kilometers to roughly 200 kilometers. China has invested about $50 billion, and they expect to get a return of $500 billion in 7 years. Again, it's all about economic. Now, you may be surprised to know its recent India-China conflict is not about land, but it is for the water bodies which are required for semiconductor development of semiconductor devices. I will elaborate on that. And China has occupied our Aksai Chin, which is controlled by them, which was lost by India in 1962 through Pakistan has gifted them. Of course, remainder part is now controlled by India. Now, there is that strip called 963 strip, which is a valley which was gifted by Pak to China. And in that valley, you have that Galwan, Siachen, Saksham. You must have heard recently all these names. And it's all about these occupying these galleys which have relevance to semiconductors. Why? Because these valleys together have roughly more than 500 glaciers of fresh water bodies. And if you want to develop a semiconductor foundry or a manufacturing facility today, it uses about 2 to 4 million gallons of ultra pure water per day. So you need a huge water resources for making semiconductor chips. Now, China is trying to develop this semiconductor device, which is in the huge demand going to be in the future wars, which is called kill switch, which is a semiconductor kill switch. What is a kill switch? Kill switch is any manipulation of the chip's software, silicon semiconductor software or hardware that would cause the chip to die outright or to shut off, for example, F-35 missile launching electronics, for example. A backdoor, by contrast, lets outsiders either gain the access to the system through the code or hardware to disable or enable a specific function. Because of this method works out without shutting down the whole chip, users remain unaware of the intrusion. An enemy could use it to bypass the battlefield radio encryption, for instance. The semiconductor kill switch, I will just give a brief. It all started in 2007 when Israeli jets bombed suspected nuclear installation in Syria. Among the many mysteries which is still surrounding that strike was the failure of a Syrian radar, supposedly which was state of the art at that time, why it could not detect the incoming assault. It was long before military and technology bloggers concluded that this was an incident of electronic warfare and not just any kind. Finally, Israel admitted the suspecting this is Syrian radar nuclear reactors in 2007. Now, commercial off-the-shelf microprocessors in the Syrian radar might have been purposely fabricated with a hidden backdoor inside by sending a pre-programmed code to those chips. An unknown maybe antagonist had disrupted the chip's functions temporarily and blocked the radar. Then recently there was some calm in this. Recently in 2016, there was a news item in the open press where it was shown that most expensive US destroyer, Navy ship broke down in Panama Canal. And in the same year, another UK daring clad destroyer suffers propulsion failure. Then Bloomberg Business reported they launched an investigation and they concluded that China was behind it and used tiny semiconductor chips to infiltrate top US companies. A super micro conduit through this Amazon and Apple were used. And recently, then Asian Review reported that TMSC, Taiwan Manufactured Semiconducting Foundry, which is the world's topmost semiconductor foundry for fabricating these chips, and they halted the chip supplies to China. Why? US wanted to starve this Huawei of chips so that to stop its 5G market dominance in the region. So now recently we can see clearly that semiconductors are a weapon in US-China trade war. TMC, which is the world's largest chip maker, halted all supplies to China, and they lost their even biggest business order in that respect. China is hungry for chips. It imports far more chips than any other country we know. So China's semiconductor market size is about $200 billion and is about 60% of the whole world. More than 90% chips are imported. Now China has an existential crisis. It has 1.5 trillion 5G rollout in 90 countries, which is under threat. Though they need unrestricted access to fresh waters to make these microchips. So Ladakh has a natural bodies. That's why they probably attacked us in this Ladakh. What they did, everybody knows. Because India had constructed some strategic roads in the last 6 years. Important one was that which everybody knows, it is now in the open press, from Leh to Daulat Bagh Old Airfield, which occurred the China. So what is the lesson? Lesson is new future walls will be cyber walls, kill switch, or which they call electromagnetic pulse. It will be not water, it will be not on the land war, it will be for the water bodies, because construction of dams and freshwater access, economics, not politics, trade war. Semiconductor microchip, according to me, will be the new oil, as to say. And even why it happened, the chip makers in US in early 70s, they try to offshore their most of these fabrication facilities to Taiwan and other labor cheap intensive countries. But what they found when the chips were coming back, then the chips can be compromised in their security and strategic use. The US realized that it no longer controls the manufacturers that go into the components of their increasingly complex systems. A single plane like Defense of Department's next generation F-35, for example, can contain hundreds of chips and with the aircraft design. So now there is a strong research and for the semiconductor people, how to test the integrity of the chips which you get. For example, in India, we are considered to be a IT power. In Bangalore, we have a lot of chip design expertise. But ultimately, we go for fabrication to these foundries. We don't have a foundry. Dr. Zarabi can tell you about as far as India, it has only one government foundry, that is Semiconductor Complex in Chandigarh. So you are dependent on for the state-of-the-art foundries which are lying outside our country. Now, question is, how do we check these, whether we send, once we design, as a designer, I design the chip, chip comes back to me, I will measure the functionality of the chip, I will find the chip is fine, it's working, whatever specs I had designed. But I don't know what the foundries have been, it has been now proven. They, while in the fabrication, they are also the people and experts. They implant some circuitry into the fabrication in such a way such that it doesn't disturb your functionality of the chip. When the chip comes back to you, you measure various functions, it functions, you don't suspect anything. But that circuitry, which or kill switch circuitry I would call, which has been implanted, they can be controlled by the hostile countries or hostile enemies as per their will, as was shown in that Syrian attack by Israeli, as I said. So what the lesson is, now every country has to, because the problem is you cannot set up your own foundries. That's a huge $1 billion investment, and managing that in a profit manner is a really tough job. As Dr. Zarabi can throw, he is there, he can throw more light on that. So now the only possible solution, what even US, like a developed country like US is doing, you develop the technologies or the methodologies to check when that you get the chips fabricated. Designers have to somehow verify whether the chip security has been compromised. That's the future. So I am sure the students who have learned these semiconductor courses here, they will go and work in some areas, and our country, whosoever in government departments, we are starting some huge programs are being started. They will contribute there to the security of the country. So that's the importance of these semiconductors. And as you know, every household is having somehow using these semiconductor chips nowadays. So that's what the importance. So I'm sure the students will take this feedback. That's what I am telling for every strategic country. Now this semiconductor is future wars are going to be about this development of semiconductor chips. Thank you.
Thank you, Professor Van. Thank you.
Thank you, sir.
Thank you.
Professor Van, thank you. It's not only the defense. Few days before, I was watching that BBC or some channel that transport industry were beating head for these chips and semiconductor shortage. Transporters, transporting.
That is for a consumer application. That is anyway okay. But for strategic defense of the country, if you want to survive as a country, your whole infrastructure, electronic warfare has to be secure. So for that, first you have to secure your country. So that for that, this semiconductor is becoming very important.
No, but what good thing have been told by the speakers is that now semiconductors have made a walkway in the medical sector, in the biological sciences also. So the humanity will get a relief.
Yes. Of course, they are developing those memory registers, neurons. They are dying that eye.
Yes.
This bionic eye. They will all use these semiconductor devices.
Niklesh, go ahead. Go ahead, Niklesh.
Okay, sir. Daraksha.
Professor Nazir. Professor Nazir. No. Go ahead.
That was really very useful. Now that we have our esteemed director with us, Professor Rakesh Sehgal, so I would like to request sir to kindly address us all on this last day, the session. So over to you, if you're there.
Yeah,
Honorable
Dr. Zarabi Saab, our Honorable ex-Chairman, Board of Governors, Professor Jagdish, Professor R.K. Bhan, other distinguished speakers for this wonderful course, Dr. M.A. Shah, who is the brain behind this course, very enthusiastic person, Dr. Prince Ganai, head of the physics department, all those involved as a team for the organization of this course. And dear participants, a very good afternoon to all of you. I attended the first session, that is the inaugural session, on 1st May. And today I attended this session from 11:45 onwards. And I was listening to the wonderful talk by Professor Jagdish. It's really very eye-opening for me also. And what all I could understand as a mechanical engineer, it's really wonderful for me also, as a to gain the knowledge. And we have of late, of course, I'm a tribologist by profession, I'm a mechanical engineer, but of late we have also started working in nanomaterials. We are working in some biomaterials also now, because we have good facilities of not only the development but also fabrication of the materials and then testing of the materials in NITS, all due to the efforts by my colleagues, by my faculty colleagues at NIT Srinagar. And really, I feel, and then listening to Dr. R.K. Bhan's lecture, it's eye-opening. I was just thinking, how much we are dependent on others for fabrication. Today morning, I was talking to my son, who is pursuing doctorate at Texas Austin. He is also a chip design engineer, and today morning he told me that there was a tape out, and probably they designed one chip and it was sent to some Taiwan some company for fabrication. And I was just thinking, what if they will introduce some circuit, which ultimately will compromise with the security of that, all those things suddenly flashed in my mind. Really, it's really very great thing, we cannot control all the things. Certain things, we can design certain things, but then the person who are fabricating that for us may introduce some bug in that, which ultimately they can control from their end. And these are very important aspects which all must think. Defense, of course, India is a huge country, and we must think of its our own defense, and we must build facilities, where we can be self-reliant on this. Probably Honorable Professor Jarabi will throw more light on this, because he has been associated with Semiconductors Limited, Mohali, Chandigarh, for a long time, and as its chairman, and he will tell us more about this. But all these things are really eye-opening. Sometimes back, it never used to be a more than PNP or NPN junction diode for me, as a science student. But now, after listening to Professor Jagdish, and then listening to R.K. Bhan, I feel I missed all these 3-4 days. Probably I should have joined this course right from the beginning, and done it along with the other participants. Attended it along with the other participants. Probably today I would have been more, knowledgeable about that. But anyway, I still feel that Professor M.A. Shah must have, recorded all the lectures, and I will request him to the recording, so that I can listen to this, the wonderful talks by all the experts, and probably I can gain some more knowledge in the field. But I was just seeing the comments on the chat box. It's really all participants are very happy. I don't know how many of them have really joined, but whatever comments they are giving, they are really wonderful. They are very encouraging for all of us, and that shows how much more we need to do, how much more need to be done for the research scholars, for the teachers, for the research community, and for the student community of this big nation. We need to frequently organize such courses, and we need to make more and more people to join and get benefited from this type of courses. After attending for half an hour session, if I can gain this much of knowledge, and if I can be so much interested, then I can feel the enthusiasm in the participants who were there all through the 5 days. It's really all credit goes to Dr. M.A. Shah and his team, and the physics department as a whole, and the experts too, people like Professor Jagdish, Dr. R.K. Bhan, and others who have delivered lectures during the course of this wonderful program. I'm really grateful to them. And, once again, I would like to congratulate Dr. M.A. Shah, his team, and the physics department. And I'm grateful to all the experts. Thank you. Thank you very much.
Thank you, sir. Thank you, sir. Thank you, sir. Thank you, sir. Thank you. Really, we are lucky. I don't know, it's a clean heart and a clean brain. I got all great speakers. And then finally, Professor Zarabi Saab accepted our invitation, whom we wanted to see him. Accepted our invitation. So he usually. Thank you, sir. Thank you. Niklesh, please.
Thank you, sir. Thank you for taking your precious time out for all of us. Thank you so much. Now, I would request Professor Mohammad Shafi Mir sir, to kindly introduce our chief guest for the day, Dr. M.J. Zarabi, sir. Kindly, please. Over to you, sir. Mohammad Shafi Mir, sir, Professor.
He's in.
Am I audible?
Yeah.
Yeah.
Yes, sir.
Yeah, you are audio.
Okay.
Make your video also, sir.
Yeah.
Make your video also. Okay.
Yeah, am I not? I am visible myself on the screen.
No, you are not visible. Make your video, sir, also. Shafi sir को unmute कीजिए.
Sir, did sir. Sir, he is unmuted.
Yeah. Okay.
Am I okay now?
Yes. Please go ahead.
Okay. It's my great honor and pleasure to introduce Dr. Zarabi this gathering. Dr. M.J. Zarabi, an eminent engineer and a versatile administrator, was born and raised in Srinagar, J&K. Son of the soil, Dr. Zarabi is a luminary in academic and in corporate sector. Doctorate in electronics from Indian Institute of Sciences, Bangalore, with more than 3 decades of experience in the field of microelectronics. Dr. Zarabi has been an enthusiastic and committed researcher with natural ability to appreciate and inspire engineering and science. He has a distinguished academic record in engineering, and it was for his excellent contribution in engineering that he was awarded the Alumni Medal of II Bangalore. In 1997, he has been honored with Scientist of the Year award for his contribution in the field of microelectronics. He has led successfully a number of technology development projects and was responsible in building VLSI fabrication facility showcase of countries' integrated chip manufacturing capability. Under his dynamic leadership, he has also established centers to manufacture monolithic microwave integrated circuits and micro electromechanical systems, and was responsible for the company being selected as foundry or MEMS under the Government of India's national program on smart materials. Upon superannuating from Semiconductor Complex Limited in August 2005, Dr. Zarab turned into a freelance consultant and has been advisor to a few companies besides being on the board of directors of a number of companies, both in and private sector. That includes Masam Electronics Private Limited, of which he is the founder chairman. At the age of around 74, he is as active as chairing expert committee meetings, answering research queries, and doing a host of other academic things, all with ease. In addition, Dr. Zarabi has co-authored a book on electron devices that gives a unique treatment to the subject, and also co-authored an IETE series book. besides having number of publications in international journals.
May I again request you don't have to read all of that. Thank you so much.
Sir, little bit.
Sir, let him complete, sir. Let him complete.
Sir, let me continue for 2 minutes more.
Continue.
And former Vice President of the Indian National Academy of Engineering, Fellow National Academy of Science of India, and Fellow Institution of Science and Telecommunication Engineering. Due to his excellent academic record and an equally impressive record of industrial achievements, Dr. Zarabi was nominated Honorable President of India as Chairperson, Board of Governors, National Institute of Srinagar, a period of 3 years with effect from 24/11/2014. Upon taking over as chairman of this prestigious institution of the country, the NIT Srinagar fraternity have seen Dr. Zarabi a principled, upright, and an employee-friendly administrator. Tender-hearted, great human being, Dr. Zarabi having unique qualities of addressing chronic issues and guiding for innovative ideas for academic excellence and research. Remember how he remained patient and camped within the campus during difficult times, be it restructuring of employees, reformations in academics, and training graduation of faculty or non-teaching. Zarabi remained always eager and at the forefront. He has been instrumental in creating a conducive atmosphere in NIT Srinagar campus for the coexistence of students that came from all parts of the country, varied backgrounds. During his tenure as chairman, DOG NIT Srinagar, the institute made ample progress in the area of infrastructure development and outreach to industry and society. He has been instrumental in creating of MOUs with NIT Srinagar and institutes like IIT Delhi, IIT Jammu, etc. Mr. Zarabi has proactively fostered and developed the atmosphere in the institute by creating facilities like Central Research Facility, Lab, of Housing and Research Facility. Innovation, Entrepreneurship Development Center of the institute is entirely his brainchild. It was his efforts that number of PhD programs started in NIT during his tenure, like MTech Engineering, MTech Geotechnical Engineering, MSc Physics, and many others. Sir, every member of NIT Srinagar fraternity loves you. Continue to do so. It is our great pleasure and honor to have Dr. Zarabi with us today in this session of the STC.
Everyone, let me say it in Kashmiri.
Yes, sir.
Kashmiri. Shafi sahab, daman chi kashres mazman. Namara korna se kabil mohabbat means ke harjal aziz. Lovable. आप मोहब्बत के काबिल हैं सर. साइकिल साहब.
Yes.
Cycle sir.
Yeah.
We are giving him the title Kabli Mohabbat. ये मोहब्बत काबिल एहतराम तो है ही लेकिन प्यार के लायक भी है. भूखे हैं.
Let me say good afternoon to all of you. My congratulations to NIT, specifically Dr. Rakesh Sahgal, and of course, more importantly, my compliments to Dr. M.A. Shah and his team for organizing this short-term course on what they have titled, which is a mouthful, Physics of Semiconductors, Smart Devices and Intelligent Automation. I would indeed request that more such things be done by NIT. This is a great service. Keep up this initiative of spreading knowledge that is, of course, my advice. And once again, my compliments to Dr. Shah and his team. My own journey in semiconductors, I'll be brief because, we are these days, unfortunately, running out of oxygen in the country. And I hope my phone does not run out of oxygen. my own journey in semiconductors started when I was doing my Bachelor of Engineering at Jabalpur. And by the way, Jabalpur happens to be one of the three, at that time, happened to be one of the three institutes, including Indian Institute of Science, Bangalore, that used to offer a BTech course in electronics and communications. So I learned my basics of semiconductors there during my final year. Otherwise, earlier years, I have worked there only with vacuum tubes. Many of you, I'm not saying most of you, many of you may not have even seen them. And from Jabalpur, I went to IIC, that was mentioned as part of my resume. And that is where I developed specific interest in semiconductors. I must tell you, while I was very proud of my teachers at Jabalpur, but I had to unlearn some of what I had learned insofar as semiconductors is concerned. I kept asking questions of myself and of my teachers about the basics. For example, the idea of holes was something that I had not quite understood, I realized. And it is only upon thinking during my Master of Engineering, and of course, with the help of my teachers, I developed a better understanding of basic semiconductor physics. And then, and that's why I'm saying this for the benefit of young students, that the basics are most important. I urge you to pay attention to the basics. Skills are important, skills you should learn, but basics to my mind is more important. I mean, when I say of the holes, for example, after, I joined SCL, when I would interview young students in SCL, most of them, when I would ask a question about why is hole mobility lower than electrons, and they would start writing an equation. Likewise, many other similar questions. I always appreciated, like to understand the basics, and that's why I'm saying that. And it is that urge within me that led to me writing that book on physical electronics, where we talked about all electron devices being the result of the behavior of charged particles in various states of matter and at their interfaces. I'm not going to elaborate this. So it's been interesting. I mean, I'm starting my own journey. I'm not going to be talking about what we have heard, read about the journey of semiconductors, starting from Bell Labs to Shockley Labs to Stanford, and what happened after the invention of transistors and the IC. I'm talking briefly about my own journey. I had this opportunity after finishing my PhD to join Electronics Commission of Government of India, where I had this opportunity of proposing setting up of Semiconductor Complex Limited. And I, having proposed that, Professor M.G.K. Menon, who was the chairman of Electronics Commission those days, is having proposed it. Now you better make sure that you set it up. So they made me officer on special duty, and I was kind of given the charter of establishing the Semiconductor Complex Limited. Of course, that also included, as I say lightheartedly, recruiting my own boss. I happened to be, I thereby became employee number 1 in Semiconductor Complex Limited and retired as they read out of my resume, retired as chairman cum managing director of the company after a stint of about 13 years as chairman cum managing director. Thereafter, I started what I call second innings of my career. I came to Delhi. I printed a card, called myself an independent consultant. Then of course, I consulted with a few companies. I also co-founded a small chip design services company, and so on. I don't think I'm going to be wanting to spend all of my time telling you about it. Now, in so far as the journey of semiconductors is concerned, from physics to devices, in Semiconductor Complex Limited, which we of course started with collaboration with American Microsystems Incorporated, starting off with production of chips with 5-micron CMOS technology. But we then, on our own, developed next generation technology, series of technologies, and also importantly, many products. Maybe as many as 5 to 6 standard products, but until I was there, about 100 odd application specific ICs, both for commercial applications and of course strategic applications. As it was mentioned, SCL still happens to be the only showcase of semiconductor or microelectronics activity in the country. After my retirement, I have also been associated with Government of India in some committees, particularly a committee relating to finding prospective investors to invest with Government of India's help to set up fabrication facilities here. We had at one time approved 2 consortia, but unfortunately, because of lack of funding, those did not come up. We have more recently, 3-4 months back, advertised, sent expression of interest from the government, and some proposals have probably been received, but I'm not too sure how good is the response. And we'll get to know soon enough how good the response is, and we may then be able to take a decision about setting up a fab here. When I say a fab here, that is meant to be what I would call a commercial fab, large scale, which will produce chips on large scale and meet at least some significant fraction of the total demand of chips in the country. That's basically the idea. Well, I do not want to stand between you and the lunch. I must once again compliment Dr. Shah and his team for organizing this wonderful short-time course. I also must take this opportunity. This has been organized in the holy month of Ramadan. So I extend my greetings to all of you on this occasion. I have now realized that the response, as I logged in this morning, the response to this course has been very good. You had participants from all over the world. What is more important is also the great speakers. I also had the opportunity of listening this morning to, only for a little while, Professor Shenoy, but almost entirely Professor Jagdish. I was very, very impressed with what I heard from them. My grateful thanks to them for having agreed to speak at the short-term course. And in fact, I would request, if it is possible, a copy of the presentation of Professor Jagdish. Now, the reason I'm saying this, because I have lately got also somewhat interested in compound semiconductors. In fact, our expression of intent that I was talking about also invited proposals for compound semiconductor fabs. So we might have something to do with that, and I would very much appreciate being in touch with Professor Jagdish. And with that, may I say thank you for inviting me to this valedictory function. I mean, there's so much more I could talk, but honestly, I don't want to be talking about, my journey. I must only say that it has been very interesting, very satisfying, and I have done whatever was possible to be done. And while I was there at SCL, I'm as I said, pretty satisfied by what we achieved. And of course, it is in good hands these days. And I mean, they have been continuing the good work, and I expect them to continue doing well. This is a government organization and not a large one. And the large one will hopefully come out of the expression of interest. Well, thank you. I noticed that I'm kind of almost out of the screen. So is that okay, Professor Shah, if I kind of say thank you once again?
Sir, we are blessed. We are blessed, sir. We are blessed, sir. On behalf of NIT Srinagar,
thank you,
sir. I do not have words. I fall short of words at times. And now this time also, I fall short of words how to thank you, sir. Professor Sahgal, please.
Thank you, sir. Thank you so much for agreeing to our request to be the chief guest.
I mean, it was
so
good to hear Dr. Rakesh Sahgal say that you are very enthusiastic. I have said on some occasion that you are yourself, Professor M.A. Shah, an inspirational speaker. Keep it up. I think spreading the knowledge, this initiative that NIT has, I feel very proud of having been associated with NIT and having known many of you. Please keep up this good work of spreading knowledge. Thanks once again.
Thank you, sir. Thank you, sir. Thank
you so much, sir. Thank you so much, sir, for taking your precious time out and gracing us all with your words of wisdom. Now, finally, we have an amazing woman with us. I personally refer to her as Wonder Woman, women of strength, our dearest Professor Seeman Rubab. I would request Rubab ma'am to kindly extend a vote of thanks to our speakers, our guests, and conclude the short-term course. Ma'am, over to you, please.
Thank you, Daraksha, for this lovely title. It's my pleasure and privilege to thank everybody associated with this extremely useful STC on behalf of Physics Department of NIT Srinagar. First of all, I would like to thank all distinguished professors, our speakers of this STC, particularly our erudite scholars from this morning session, Professor M.R. Shenoy from my alma mater, IIT Delhi, took us through the basics of semiconductor devices. Then Professor Chennupati Jagdish exposed us to frontiers of semiconductor devices in all sorts of applications, including LEDs, lasers, nanowires, solar cells, neurons, and so on and so forth. We are proud that our alumni, one of our alumni from NIT Srinagar, Anha Bhatt, is working in his group. We also like to thank him about the useful information about Chennupati and Vidya Jagdish Endowment Fund initiated by him and his wife for Indian students. Next, I am grateful to today's guests, Dr. Zarabi. I was so happy to see you, sir. We have seen you here in our institute physically, and now at least I saw you after so many years through your video interaction. And We are very happy that you spared your valuable time, and we are inspired by you that you are still continuing. You have not taken that is what we call superannuation or retirement. You are still working. And my good wishes to Ma'am Zarabi sir also. Yeah, I have met her personally, and so sir, please extend my good wishes and greetings to her also. And then our alumni, Dr. R.K. Bhan, he opened our eyes regarding the usage of SC devices and chips in defense, and it was illuminating and eye opener, sir. And we would sometime like to have a full-fledged talk in our department on that regard. Sometime we will again invite you, sir. So we are really thankful. Then I would like to thank Semiconductor Society of India, who were a co-host of this event, and we have speakers from their organizations and and they have always, whenever we have requested them for co-hosting, in way back in year 2005 when I organized International Year of Physics, they also provided monetary support in that event also. So thank you so much, Semiconductor Society of India. Next, I would like to thank our administration for allowing us to organize this STC. In particular, we express our gratitude to our director, esteemed director, Professor Sehgal sir, registrar, Professor Bukhari sir, our HOD, Professor Ganai sir, HOD Mechanical Nazir Sheikh sir for joining us, HOD Alumni, Professor M. Shafi Mir sir for joining the valedictory session, sparing your valuable time. And then it's my pleasure to thank the very alert and inquisitive participants. They have made this STC vibrant, interactive with their questions. Love you all, dear participants. I feel proud now to be a colleague of my dear friend Ashraf Shah. He gave us this lovely opportunity to interact with so many erudite professors. Hats off to you, my dear friend. Last but not least, I'm so proud of our all MSc students, especially Niklesh and Daraksha. Niklesh has raised the bar high for new students to emulate. So our the fresh MSc students has to compare to his abilities. So Niklesh, we are going to miss you. Like you are a final year student, we are going to miss you, but we wish you will always be connected to us in our various program as a participant wherever you go for your PhD. We wish you all the best.
Thank you, ma'am.
Love you. If I have inadvertently missed anybody who has contributed in organization of this short-term course, my gratitude to them. And और आखिर में मैं तमाम लोगों से इजाजत लेना चाहूंगी और तमाम का तहे दिल से शुक्रिया अदा करना चाहूंगी सभी लोगों का, और जो हमारे मेहमानाने गिरामी हमारे साथ शामिल हैं. I hope Shenoy sir understand and this Jagdish sir they understand a little bit of Urdu, sir. So हम तहे दिल से आपका शुक्रिया अदा करना चाहते हैं सर. और तमाम लोगों से इजाजत लेने से पहले मैं दरखास्त करूंगी कि स्पेशली जो लोग इंडिया में हैं वो अभी जो कोविड से परेशान हैं तो वो अपनी हिफाजत करें, मास्क लगाएं और बिला जरूरत बाहर ना निकलें. शुक्रिया. नमस्ते.
Thank you very much. Thank you.
Thank you, everyone.
Thank you, Professor Jagdish Saab. Thanks.
Thank you. Thank you all. Thank you. Bye-bye.
so much.
Thank you. Bye-bye. Bye-bye.
Thank you, everyone, for
Dr.
being with
Zarabi, I'll
us.
send you my slides. Dr. Zarabi, I'll send you my slides. Thank you very much. And then I'll ask Dr. Shah to send me your email address and I'll send you my slides. Thank you very much.
Thank
I'll
you.
do
Thank
it.
you,
I'll
Professor
connect you, sir.
Jagdish. Yes. Yes. Thanks.
I'll connect you to director, sir. Also, he may need the slide.
Yeah. Good. Thank you so much. It was a pleasure listening to
Thank you.
Yeah.
Bye-bye. Thank you.
Dr. Prince, with your permission, we are concluding. Dr. Prince.
Okay.
We are concluding. Thank you. Thanks. Zarabi Saab, thank you, sir. Thank you.
Thank you. My pleasure. My pleasure.
Thank you. Convey adab, sir. Convey adab. Thank you.
Thank you. Thank you all of us for being with us
Something to say.
and making it a huge success. I would also want to take some moment to shed some light on the present scenario around. As we are well aware of the situation, I request all of us to kindly follow all the precautions and help each other during this crisis. Because over centuries, through storms and strife, in peace and war, we have come so far and we have to go far, right? So we need to help each other and follow SOPs. So you all stay safe and we'll overcome this together. And congratulations everybody for making this program a huge success for all of us. So cheers everybody. Bye-bye. Thank you. Thank you, sir.
Okay, good.
Thank you, sir.
Thank you.
I'm proud to have junior one, Daraksha. Junior necklace. Yeah, that nursery has been made. Thank you, Daraksha. Thank you. Thank you all. I'll end the meeting now.
Sir.